Hello there, and welcome to Just About Earth, where curiosity gets comfortable, the lights grow a little softer, and the long story of our planet is allowed to unfold without any hurry. Tonight, we're turning toward a question that sounds simple at first, but becomes much larger the longer we sit with it. How long will it be until the next ice age begins? Perhaps you are listening beneath a warm blanket with rain at the window, a fan humming nearby, or a cup of tea slowly becoming colder than you intended. Wherever you are, take a moment to notice the temperature around you. Does the air feel warm tonight? Is there frost outside? Are you in the middle of summer, winter, or one of those uncertain weeks when the weather seems to have misplaced the calendar? And where in the world are you listening from right now? It is a fitting question, because the climate around us often feels immediate and personal. We notice the cold when we step outside without the right coat. We notice the heat when the bedroom refuses to cool down. We complain about the weather with impressive consistency, even though none of us has ever been placed in charge of it. But the climate of Earth moves on scales so large that a human lifetime is barely a moment. A cold winter can feel severe. A warm decade can feel permanent. Yet the planet has passed through changes far greater than anything one person could witness from beginning to end. If you find these quiet journeys through Earth's history soothing, interesting, or simply useful for keeping the day's noise at a respectful distance, you might like the video and subscribe to Just About Earth. It helps this calm corner reach other curious listeners who may also enjoy falling asleep while thinking about glaciers, ancient oceans, and the occasional mammoth. And do not worry if you drift off before we reach the answer. The ice is not expected at the front door before morning. The phrase Ice Age usually brings a familiar picture to mind. Vast white sheets cover northern lands, woolly mammoths cross frozen plains, human families shelter from bitter winds beneath heavy animal skins, mountains disappear under glaciers, and the world seems locked in a permanent winter. It is easy to imagine an ice age as a sudden catastrophe, a wall of cold moving south while everyone looks for thicker socks. The real process is slower, more complicated, and in some ways more surprising. Ice ages do not normally begin in a single winter. They grow over thousands of years. Snow survives one summer, then another. Ice gathers in places where more falls than melts. Bright frozen surfaces reflect sunlight back into space. Ocean currents shift. Vegetation changes. Carbon moves between the atmosphere, sea, soil, and living things. A small cooling influence can become stronger as different parts of the climate system begin to reinforce one another. There is also an important detail that can make the whole subject feel slightly confusing. In a technical sense, Earth is already living in an ice age. An ice age is not defined as a time when the whole planet is frozen. It is a long interval when permanent ice exists at the poles. By that definition, the present ice age began millions of years ago and continues today. Greenland and Antarctica are not temporary winter decorations. They are enormous stores of ice that have remained through many changes in global climate. Within this larger ice age, Earth moves between colder glacial periods and warmer interglacial periods. The colder phases are the ones most people mean when they say ice age. During those times, huge ice sheets spread across large areas of North America, Northern Europe, and Asia. Between them come warmer intervals like the one we live in now. Our present warm interval is called the Holocene, and it began after the last major glacial period ended roughly 12,000 years ago. That may sound like a very long time, and for human history it certainly is. Farming, cities, writing, trade, kingdoms, industry, and the entire modern world developed during this relatively mild stretch of climate. But compared with the full rhythm of glacial cycles, 12,000 years is not especially long. Some earlier interglacial periods lasted longer. Others ended as slow changes in Earth's orbit reduced summer sunlight in the far north, allowing winter snow to remain and ice sheets to begin growing again. This is where the central question becomes more difficult. If ice ages have returned again and again, should another cold phase be approaching? Are we living near the end of a warm pause? Could glaciers begin advancing in a few thousand years? Or has the atmosphere changed so much that the old schedule no longer applies? The answer is not written on a single clock. Earth does not have a neat glacial alarm that rings every 100,000 years while the planet reaches over and presses snooze. The timing depends on several slow astronomical cycles, the arrangement of continents, the behaviour of oceans, the amount of carbon dioxide in the atmosphere, and feedbacks involving snow, ice, clouds, plants, and dust. These influences operate together, sometimes strengthening one another and sometimes pulling in different directions. Long before humans built thermometers or satellites, Earth was already responding to changes in its journey around the Sun. Our planet's orbit is not a perfect, unchanging circle. Its shape varies slowly. Earth's axis also changes its tilt, and the direction of that axis gradually turns, rather like a spinning top that traces a slow circle as it wobbles. These movements alter where and when sunlight reaches the planet most strongly. The amount of summer sunlight falling on high northern latitudes is especially important. This may seem odd at first. If an ice age is cold, surely winter should be the main concern. But a snowy winter does not create a great ice sheet if the following summer melts everything away. What matters is whether summer becomes cool enough for some snow to survive. When it does, the next winter adds another layer. Over many centuries, those layers can thicken into lasting ice. Imagine leaving a small patch of snow in the shade at the edge of a garden. If each warm season removes it completely, nothing accumulates. But if a little remains and more snow arrives the next year, the patch can slowly grow. A continental ice sheet follows a far grander version of this idea, although the garden is the size of a country, and the process is not ideal for the flowers. The orbital cycles that influence this pattern are often associated with the Serbian scientist Milutin Milankovic, who worked out how long-term changes in Earth's movement could help pace the advance and retreat of ice. His calculations gave scientists a way to connect variations in sunlight with evidence preserved in ocean sediments, ice cores, fossil pollen, and ancient shorelines. These records show that the climate has not moved in a simple repeating circle. It behaves more like a system with several overlapping rhythms. One cycle may favour cooler northern summers, while another works against it. The atmosphere may contain enough carbon dioxide to resist cooling. Ice sheets themselves can reshape winds and ocean circulation once they become large. A small astronomical push can matter greatly at one time and produce a weaker response at another. That is why predicting the next glacial period is not as easy as extending a line on a calendar. It is less like knowing when sunrise will occur tomorrow, and more like trying to predict when a very slow set of gears will finally move a large machine, while some of the gears are being changed. For much of the 20th century, some discussion suggested that the present interglacial might naturally end within several thousand years, or perhaps a few tens of thousands of years. The exact estimate depended on which past period was considered the best comparison and how scientists treated the orbital conditions ahead. But there was always a major complication. The level of carbon dioxide in the atmosphere was already different from that of earlier natural cycles, and industrial activity was increasing it rapidly. Carbon dioxide is only a small part of the atmosphere, but it has an important effect on temperature because it absorbs and re-emits heat. Natural changes in carbon dioxide helped amplify past glacial cycles. When the climate cooled, oceans and ecosystems shifted in ways that lowered atmospheric carbon dioxide, encouraging further cooling. When the climate warmed, carbon dioxide rose and strengthened that warming. It was not the only cause of the cycles, but it acted as a powerful partner. Human beings have now added a large amount of carbon dioxide by burning coal, oil, and natural gas, producing cement, and changing forests and landscapes. This has altered the starting conditions under which the next natural cooling would have developed. The slow orbital influences have not stopped. Earth still tilts, wobbles, and follows its changing path around the Sun. but they now operate within an atmosphere carrying much more heat-trapping gas than it did before industrialization. This means the question of the next ice age is no longer only about astronomy. It is also about the long-lasting effect of human activity. Some of the carbon dioxide released today will remain involved in the climate system for a very long time. A portion will be absorbed by oceans and land, while another portion will continue influencing climate across many centuries and beyond. The exact future depends on how much more is released, how quickly emissions decline, and how the planet responds. The strange result is that human-caused warming may delay the next glacial period for tens of thousands of years, perhaps much longer under high emission scenarios. The next great spread of northern ice may not arrive on the natural timetable that would have applied without industrial carbon emissions. Instead, the current warm interval could be extended far beyond the length it might otherwise have reached. This does not mean winter will disappear, that snow will never fall, or that every place will become steadily warmer in a simple way. Weather will continue to vary. Cold outbreaks will still happen. Regional climates may shift in complicated directions as ocean currents and atmospheric patterns change. An ice age is a global, long-term state, not a single cold season or a dramatic week of headlines about frozen roads. It also does not mean that warming and cooling are equal concerns separated only by different preferences for coats. A rapid rise in global temperature over centuries is very different from the slow approach of a glacial period over thousands of years. Human societies, coastlines, farming systems, cities, and ecosystems are adapted to the climate conditions in which they developed. Fast change creates pressure because there is less time to adjust. When people ask about the next ice age, they are sometimes really asking a second question. Could present warming suddenly reverse? Could changes in ocean circulation plunge Europe or North America into deep cold? Films and dramatic headlines have encouraged the idea that one disrupted current might freeze entire continents almost overnight. Real climate systems can change abruptly in geological terms, and ocean circulation matters greatly, but a new continental glaciation would still require persistent conditions that allow ice to build over very long periods. A slowdown in a major Atlantic circulation system could alter regional temperatures and rainfall. It could make some areas warm less quickly than others, or produce local cooling against a background of global warming. But that is not the same as beginning a full glacial period. Earth's climate can contain warming in one region, cooling in another, stronger storms elsewhere, and shifting rainfall patterns all at once. It is rarely considerate enough to choose one simple storyline. The deeper reason this topic is so fascinating is that ice ages reveal how sensitive Earth can be to small changes applied over enough time. A modest variation in summer sunlight does not sound powerful enough to build ice several kilometers thick. Yet once snow survives, ice reflects more sunlight. As ice sheets grow, they alter the height and colour of the land. Winds carry dust differently. Oceans absorb and release carbon. Sea level falls as water becomes trapped on continents. The entire planet begins responding to the expansion of ice. During the last glacial maximum, around 20,000 years ago, so much water was locked in ice sheets that sea level stood far lower than it does today. Land-connected regions now separated by ocean. Britain was joined to mainland Europe across a broad plain. Alaska and Siberia were linked by the Bering Land region. Animals and people moved through landscapes that later vanished beneath rising seas. Large areas of Canada and the northern United States lay beneath the Laurentide ice sheet. Northern Europe was covered by another great mass of ice. These were not thin winter coatings. In places, the ice rose kilometres above the land. Its weight pressed down the crust. Its movement scraped rock, redirected rivers, carried boulders, and shaped thousands of lakes. Even now, the land in some northern regions continues to rise slowly after being freed from that enormous burden. Our familiar world is therefore a temporary arrangement. Coastlines, forests, deserts, and rivers seem fixed because they change slowly compared with a human life. but Earth has never promised to keep the furniture in the same place. The ground beneath cities was once tundra, seabed, forest, desert, or ice. If we could watch the planet across hundreds of thousands of years, maps would appear to breathe. The ice would spread and retreat. Seas would fall and rise. Habitats would move north and south. Species would follow when they could. The people living through the end of the last glacial period did not have the advantage of seeing the full pattern. They experienced local changes across generations. A coastline moved. A valley became wetter. Familiar animals shifted their range. Forests entered places that had once been open grassland. The transformation of the world was enormous, but from one day to the next, life still involved finding food, raising children, repairing tools, and probably wondering why someone had used the last of the dry firewood. Today, we can combine evidence from many parts of the planet. Air bubbles trapped in Antarctic ice preserve samples of ancient atmosphere. Layers of ocean mud record changes in temperature and ice volume. Pollen grains show how plant communities moved. Cave deposits reveal shifts in rainfall. Tiny marine organisms carry chemical signs of the water in which they lived. Together, these records allow scientists to reconstruct climates that no human observer wrote down. They also show that the present is connected to a much longer story. The Holocene did not begin because Earth reached a permanent ideal temperature. It emerged from a particular arrangement of orbital conditions, greenhouse gases, ice sheets, oceans, and living systems. That arrangement has supported human civilization remarkably well, but it is not guaranteed to continue unchanged. So how long until the next ice age begins? The most responsible answer is that it is not about to begin soon, and human influence has probably pushed it much farther into the future than natural orbital cycles alone would suggest. But that simple answer opens several others. What exactly counts as the beginning? How do scientists identify the first step toward a glacial period? Which orbital pattern would normally have encouraged it? How much carbon dioxide is enough to prevent it? And can we compare our future with any earlier time in Earth's history? To understand those questions, we need to look past the popular image of one frozen world and examine what an ice age actually is. Earth has experienced several major icehouse periods, separated by warmer greenhouse worlds with little or no permanent polar ice. Some glaciations lasted millions of years. Others became so severe that ice may have reached close to the equator. The current ice age is only the latest episode in a planetary history filled with very different climates. Even within this one ice age, the colder and warmer phases have changed their rhythm. Earlier glacial cycles were often paced differently from the more recent pattern. Ice sheets did not simply appear every fixed number of years. The climate system shifted as erosion, carbon cycling, ocean circulation, and the size of existing ice sheets changed. Earth's cold periods have a history of their own. Before we can estimate when another one might develop, we first need to separate three ideas that are often mixed together: an ice age, a glacial period, and an ordinary cold spell. We also need to understand why a planet with deserts, tropical forests, warm oceans, and cities crowded with summer air conditioners can still be described as living in an ice age right now. That is where the colder part of Earth's long climate rhythm begins to come into view. When most of us hear the words ice age, we tend to imagine one particular version of Earth. The sky is grey, the wind is sharp, mammoths move across open plains, and a thick wall of ice sits somewhere beyond the horizon, slowly considering whether it would like to visit the neighbourhood. It feels like a single event, one long frozen episode that happened before civilization and ended when the weather finally improved. Earth's actual history is far less tidy. Ice ages have begun, strengthened, weakened, retreated, and returned many times. Some lasted for millions of years. Some may have covered much of the planet. Others allowed forests, grasslands, warm seas, and rich ecosystems to exist alongside enormous polar ice sheets. The climate did not simply switch between warm and cold, it moved through long overlapping rhythms shaped by the sun, the atmosphere, the oceans, the continents, and the slow movement of Earth itself. The first useful thing to understand is that an ice age is not the same as a glacial period. An ice age is a broad interval during which permanent ice exists on the planet's surface, usually near one or both poles. Within an ice age, the climate can move back and forth between colder glacial periods and warmer interglacial periods. A glacial period is the colder part of the cycle, when continental ice sheets expand far beyond the polar regions. An interglacial is a warmer pause, when those ice sheets retreat. We are living in one of those warmer pauses now. That means Earth is currently in an ice age, even though many parts of the world are warm, tropical, or sufficiently hot to make a parked car feel like a small oven. The continued presence of the Antarctic and Greenland ice sheets places us within what scientists call the Quaternary Ice Age, which began about 2.5 million years ago. Within that larger ice age, dozens of glacial and interglacial cycles have occurred. The last major glacial period reached its coldest point around 20,000 years ago. Since then, the great northern ice sheets have mostly disappeared, sea level has risen, forests have spread, and human civilization has developed during the warm interval known as the Holocene. So the world we know is not the opposite of an ice age. It is one of the warmer rooms inside it. This distinction matters because it changes the way we think about climate history. Ice ages are not brief accidents. They can become long background conditions within which the planet continues changing. A single ice age may include repeated advances and retreats of glaciers, each taking tens of thousands of years. The ice does not move according to a simple calendar. It does not spread across continents for exactly the same length of time and then politely leave. Different cycles vary in strength and duration. Sometimes the climate seems especially responsive to changes in sunlight. At other times, carbon dioxide, ocean circulation, or the size of existing ice sheets can alter the result. The Quaternary Ice Age is only the most recent cold interval in a much longer story. Geological evidence suggests that Earth has experienced several major ice ages, beginning far deeper in the past than any animal, tree, or familiar continent. One of the earliest known major glaciations occurred more than 2 billion years ago. It is often called the Huronian glaciation, named after rock formations around Lake Huron in North America, where some of the evidence was studied. At that time, Earth looked nothing like the planet we recognize. There were no plants on land, no animals, and no forests waiting to become coal. Life was mostly microscopic and lived in the oceans. The atmosphere contained very little oxygen compared with today. Then something important began to happen. Certain microorganisms, especially cyanobacteria, were using sunlight to produce energy through photosynthesis. As part of that process, they released oxygen. At first, much of this oxygen reacted with iron and other materials, but eventually oxygen began accumulating in the atmosphere during what scientists call the Great Oxidation Event. This was one of the most important changes in Earth's history, although it may have had an unexpectedly chilly side effect. Before oxygen became abundant, methane may have played a major role in keeping the early Earth warm. Methane is a powerful greenhouse gas. As oxygen increased, it reacted with methane and reduced its concentration in the atmosphere. With less methane available to trap heat, the planet may have cooled dramatically. Glaciers spread across parts of the world, possibly several times, over a very long interval. The exact causes and extent of the Huronian glaciations are still studied, but they reveal something central about Earth's climate. Life does not merely respond to the environment. Living organisms can change the atmosphere, and in doing so, alter the climate of the entire planet. Those ancient microbes had no plan to cool the world. They were simply carrying on with their microscopic business. Yet their collective activity helped transform the atmosphere. It is perhaps the earliest known example of life-changing Earth on a global scale, which is impressive for organisms that did not even have meetings. Much later, Between roughly 720 million and 635 million years ago, Earth entered another extraordinary cold interval known as the Cryogenian period. This was the age of the famous Snowball Earth glaciations. The name Snowball Earth sounds almost cheerful, as though the planet had been rolled together by an enthusiastic child. The conditions were anything but cheerful. Geological evidence suggests that ice may have reached very low latitudes, perhaps even areas near the equator. Scientists have found ancient glacial deposits in rocks that appear to have formed in tropical regions. These deposits include stones carried by ice and dropped into marine sediments, along with scratched and ground surfaces produced by moving glaciers. If ice truly extended close to the equator, then the planet may have looked almost entirely white from space. Oceans could have been covered by thick ice, although some researchers think open water may have survived in certain regions. This leads to several possible versions of the idea. In a hard Snowball Earth scenario, nearly the entire ocean surface freezes. In a softer version, sometimes called Slushball Earth, large areas remain ice-covered while belts of open water survive near the tropics. The exact picture remains debated because rocks from that time are incomplete, altered, and often difficult to interpret. Even so, the Cryogenian glaciations were clearly severe. The cooling may have started through a combination of continental arrangement, weathering, atmospheric carbon dioxide, and the amount of sunlight reflected by ice. At that time, continents may have been positioned in ways that encouraged rapid chemical weathering of rock. Weathering removes carbon dioxide from the atmosphere over long periods. Carbon dioxide combines with rainwater, reacts with minerals, and is eventually carried into the oceans, where some of the carbon becomes locked into sediments. With enough carbon dioxide removed, the greenhouse effect weakens and the climate cools. Once ice spreads, it creates another powerful influence. Ice and snow are bright surfaces. They reflect a large portion of incoming sunlight back into space. Dark ocean water absorbs sunlight efficiently. Bright ice reflects it. So as ice expands, the planet absorbs less heat. That causes more cooling, which allows even more ice to form. This is known as the ice-albedo feedback. It is one of the clearest examples of a climate feedback strengthening an initial change. The process can be compared to placing a mirror over a dark surface. The more of the dark area the mirror covers, the less energy the surface absorbs. Continue far enough, and cooling can accelerate. This creates a serious question. If Earth became deeply frozen, how did it ever escape? The likely answer involves volcanoes. Even if the surface was largely covered by ice, volcanic activity would have continued releasing carbon dioxide. Under normal conditions, weathering removes some of that carbon dioxide. But if the continents were buried beneath ice, weathering would have slowed dramatically. Carbon dioxide could then have accumulated in the atmosphere for millions of years. Eventually, the greenhouse effect may have become strong enough to warm the planet and begin melting the ice. Once dark ocean or land became exposed, it absorbed more sunlight. That weakened the reflective cooling effect and encouraged further melting. The same feedback that helped the ice spread could then work in reverse. The end of a Snowball Earth episode may therefore have been abrupt by geological standards. A deeply frozen planet could have shifted into an extremely warm climate, with intense rainfall, rapid weathering, and oceans receiving large amounts of dissolved minerals. Rocks known as cap carbonates are often found directly above Cryogenian glacial deposits. These carbonate layers may record the unusual conditions that followed the melting. They suggest that the transition from severe glaciation to greenhouse warmth was not a gentle return to pleasant spring weather. It was more like turning the thermostat from freezer to tropical greenhouse while the room was still defrosting. The Cryogenian period is especially interesting because complex life expanded after these glaciations. The relationship is not completely understood, and scientists do not claim that freezing the planet automatically produces animals. Still, the environmental changes associated with glaciation, melting, nutrient movement, and rising oxygen may have influenced the conditions in which more complex organisms evolved. After the Cryogenian came the Ediacaran period, when some of the earliest large complex organisms appeared. Later, during the Cambrian period, animal life diversified dramatically. The cold world did not remain lifeless. Instead, the planet eventually emerged into a biological transformation. Earth experienced another major cold interval from the late Ordovician into the early Silurian period, around 440 million years ago. This event is sometimes associated with the Andean-Saharan glaciation because evidence has been found in regions that are now parts of South America and Africa. Those locations sound much too warm for great glaciers today, but continents move. During the Ordovician, much of the land that would later become Africa and South America formed part of the southern supercontinent Gondwana. Large areas of Gondwana were positioned over or near the South Pole. This is an important reminder that the climate of a location depends not only on the atmosphere, but also on where the land happens to be. The Sahara was not always a desert. Antarctica was not always frozen. Continents are slow travellers, but given hundreds of millions of years, they can go surprisingly far. The late Ordovician glaciation coincided with one of the largest mass extinctions in Earth's history. Sea level fell as water became trapped in ice, reducing shallow marine habitats where much of life existed. Later, when the ice melted and the climate shifted again, changing ocean conditions created additional stress. This shows that both cooling and warming can disrupt ecosystems, especially when changes happen faster than organisms can adapt or move. Life can survive enormous climate shifts, but individual species often do not. Earth continues, the membership changes. Another major cold interval occurred during the late Paleozoic era, beginning more than 300 million years ago. It's often called the late Paleozoic Ice Age or the Karoo Ice Age. By then, life on land had become far more complex. Vast forests covered swampy regions. Insects, amphibians, and early reptiles occupied the continents. Many of the coal deposits used by industrial societies hundreds of millions of years later began forming from plant material buried in these ancient wetlands. The growth and burial of plants played an important role in the carbon cycle. Plants absorbed carbon dioxide through photosynthesis. When large amounts of plant matter were buried without fully decaying, some of that carbon was removed from the atmosphere for very long periods. At the same time, continents were assembling into the supercontinent Pangaea. Large areas of land were positioned near the South Pole, allowing major ice sheets to form. Chemical weathering of newly raised mountain ranges may also have helped lower atmospheric carbon dioxide. The result was another long glacial interval, although it was not uniformly frozen. Tropical forests still existed near the equator while glaciers covered parts of the southern supercontinent. Warm and cold regions could exist together, just as they do today, but the global balance was different. The late Paleozoic Ice Age eventually ended as carbon dioxide levels rose, continental positions changed, and the climate moved toward warmer conditions. By the time dinosaurs became dominant much later, Earth was largely in a greenhouse state. During much of the Mesozoic era, which included the Triassic, Jurassic, and Cretaceous periods, permanent polar ice was limited or absent. Global temperatures were generally warmer than today. Sea levels were high, and shallow seas covered parts of the continents. Forests grew at high latitudes. Dinosaurs lived in regions that now lie within the Arctic and Antarctic. This did not mean the poles were tropical beaches all year. They still experienced long, dark winters, but the climate was mild enough to support ecosystems very different from the modern frozen polar landscape. The existence of these greenhouse worlds helps place our current climate in perspective. Permanent polar ice is not an unavoidable feature of Earth. For long stretches of geological history, the planet had little or none. So why did Earth eventually return to an icehouse state? The answer developed gradually during the Cenozoic era, after the extinction of the non-avian dinosaurs. Continents continued moving, mountain ranges rose, ocean gateways opened and closed. Carbon dioxide generally declined over tens of millions of years. Antarctica became increasingly isolated over the South Pole. As South America and Australia moved away, ocean water gained the ability to circulate more freely around the continent. The Antarctic Circumpolar Current developed, helping separate Antarctica from warmer waters to the north. By around 34 million years ago, a major Antarctic ice sheet had formed. This marked a significant step toward the modern icehouse world. The northern hemisphere remained much less heavily glaciated for millions of years. Greenland developed substantial ice, but the great repeating northern ice sheets of the Quaternary became established much later, around 2.5 million years ago. Several factors may have contributed. Carbon dioxide had declined. The arrangement of continents and oceans had changed. The uplift of mountains affected weathering and atmospheric circulation. The closure of ocean connections around Central America altered currents between the Atlantic and Pacific. Once large northern ice sheets began forming, Earth entered the glacial-interglacial rhythm that shaped recent human evolution. At first, these cycles were often dominated by a rhythm of roughly 41,000 years, closely associated with changes in the tilt of Earth's axis. Later, around 1 million years ago, the pattern shifted. The more recent glacial cycles became larger and were paced more strongly around intervals of roughly 100,000 years. This change is known as the mid-Pleistocene transition. It did not happen because Earth suddenly acquired a new orbital cycle. The astronomical variations already existed. Instead, something in the climate system changed the way it responded. One possibility is that repeated glaciations gradually removed loose soil and sediment from northern landscapes. Once ice sheets reached harder bedrock, they may have become thicker and more stable. Changes in atmospheric carbon dioxide, ocean circulation, and the internal behaviour of ice sheets may also have played a role. The result was the familiar pattern of long glacial periods interrupted by shorter, warm interglacials. For much of the last several 100,000 years, the cold phases lasted far longer than the warm ones. A glacial cycle was not simply a smooth slide into cold, followed by an equally gentle return. Cooling often developed gradually as ice sheets expanded over many thousands of years. Deglaciation could occur more rapidly as rising summer sunlight, greenhouse gases and feedbacks weakened the ice. The last glacial period was itself filled with variation. Temperatures rose and fell, ice sheets advanced and retreated, ocean circulation changed. In the North Atlantic region, large numbers of icebergs sometimes broke away and carried rocky debris into the ocean. When the icebergs melted, they dropped this material onto the seafloor. Ice cores from Greenland reveal abrupt temperature shifts that occurred within decades or centuries. These changes were fast enough to affect ecosystems and human communities, although they took place within the broader glacial climate. So even a glacial period is not one unbroken winter. It contains its own warmer and colder episodes, regional differences and sudden changes. A person living through it would have experienced seasons, mild years, severe years, droughts, storms, and ordinary daily weather. The background climate was colder, but life did not pause beneath a single grey sky. At the last glacial maximum, roughly 20,000 years ago, ice sheets covered much of Canada, parts of the northern United States, Scandinavia, and northern Europe. Mountain glaciers expanded in many other regions. Sea level was more than 100 metres lower than today because so much water was stored on land as ice. The lowered sea exposed broad continental shelves. Britain was connected to Europe through a lowland region now called Doggerland. Australia was joined more closely with New Guinea. Siberia and Alaska were connected through Beringia. These exposed lands were not merely empty bridges waiting for people to cross. They were large environments with plants, animals, rivers and changing climates. Some supported grasslands where mammoths, bison, horses and other large animals lived. Human beings adapted to these conditions using clothing, shelters, fire, tools, social cooperation and detailed knowledge of local landscapes. They did not spend every moment fleeing glaciers. Most communities lived beyond the edges of the major ice sheets, in tundra, steppe, woodland, coastal, or river environments. As the climate warmed, the ice sheets melted and sea level rose. Forests moved north. Animals shifted their ranges. Some species declined or disappeared. Human groups moved, adapted, and developed new ways of living. By around 11,700 years ago, the Holocene had begun. This warmer interval provided relatively stable conditions in many regions. Agriculture appeared independently in several parts of the world. Settlements grew, populations increased, towns and cities followed. It is tempting to think that the Holocene represents Earth returning to normal. But geology offers no single normal climate. The planet has been warmer, colder, wetter, drier, more heavily forested, more desert-like, almost ice-free and possibly almost ice-covered. What feels normal to us is simply the narrow range in which our societies developed. We are used to present coastlines because our maps were drawn during this interglacial. We are used to current rainfall zones because our farms and cities were built around them. A mammoth might have found the arrangement disappointingly warm. Ice ages therefore reveal two different kinds of climate stability. Over short human timescales, the climate may appear steady enough for people to build permanent settlements. Over geological timescales, that stability becomes temporary. The restless rhythm does not mean climate changes randomly. There are causes behind every major shift. Continents move, mountains rise, volcanoes release gases, rocks remove carbon dioxide through weathering. Life alters the atmosphere. Oceans transport heat. Ice reflects sunlight. Earth's orbit changes the seasonal distribution of solar energy. These influences operate at different speeds. Some act over millions of years. Others can produce noticeable changes within decades. Together, they create the climate history preserved in rock, ice, sediment, fossils, and the shape of the land. A deep valley may show where a glacier once moved. A boulder resting far from its original bedrock may have been carried by ice. Scratches on rock can reveal the direction of glacial movement. Ancient shorelines high above modern seas record past changes in the balance between ice, water, and land. Even the ground beneath northern cities may carry the mark of vanished ice. Landscapes continue responding to the removal of ice sheets that melted thousands of years ago. The crust had been pressed downward by their weight, and is still slowly rising in some regions. The next time ice begins expanding across the northern hemisphere, it will not be the start of something entirely new. It will be another movement within a climate rhythm that has shaped oceans, continents, ecosystems, and human history. Yet the rhythm is not a perfect repetition. The atmosphere today is different. Human activity has raised greenhouse gas concentrations. Forests, soils, and oceans are changing. The natural influences that once guided the climate toward another glacial period are now operating under altered conditions. To understand when the next cold phase might have started without that interference, we need to look beyond glaciers themselves and toward the slow, astronomical movements that help determine whether northern snow survives the summer. Earth's orbit changes shape. Its axis changes tilt, and the direction of that axis turns through space. None of these movements looks dramatic from one year to the next, but together they act as the patient timekeepers behind the rise and fall of ice. If you could watch Earth from far above the solar system for a few 100,000 years, the planet would not trace the same neat path around the sun again and again. Its orbit would slowly change shape. Its axis would tilt by slightly different amounts. The direction of that axis would turn through space in a long, gradual wobble. None of these changes would look dramatic from one year to the next, and they would not rearrange the seasons with the enthusiasm of someone spinning a thermostat. But over tens of thousands of years they alter where sunlight falls, when it arrives, and how strongly it warms different parts of the planet. These slow movements are known as orbital cycles, and they play a major role in pacing the growth and retreat of ice sheets. They do not create ice ages by themselves, but they provide the long astronomical push that can encourage a cooler climate to begin. The name most closely associated with this idea is Milutin Milankovic, a Serbian mathematician and engineer who spent years calculating how changes in Earth's orbit might influence climate. His work helped explain why glacial periods appeared and disappeared in a repeating but uneven pattern. Milankovic did not invent the idea that astronomical changes affect climate. Earlier scientists had already suspected a connection. What he did was turn the idea into a detailed mathematical framework. He calculated how variations in orbit, tilt, and axial direction change the amount of sunlight reaching different latitudes during different seasons. This was an enormous task, especially in a time before electronic computers. There were no climate models running quietly on powerful machines, no satellite measurements, and no convenient button labelled "Calculate the next 100,000 years." Much of the work involved long tables of numbers, handwritten calculations, and the kind of patience that makes waiting for a kettle seem positively reckless. The first of the major orbital changes is eccentricity, which describes the shape of Earth's orbit around the Sun. We often picture that orbit as a simple circle. In reality, it is slightly elliptical, meaning it is stretched a little. Over long periods, the orbit shifts between being more circular and more elongated. These changes occur through cycles influenced mainly by the gravitational pull of other planets, especially Jupiter and Saturn. Their gravity does not drag Earth wildly out of position, but it gently alters the orbit over time. The strongest eccentricity cycle is often described as lasting about 100,000 years, although there are also longer variations, including a cycle of roughly 400,000 years. When Earth's orbit becomes more elliptical, the difference between its nearest and farthest distances from the Sun increases. When the orbit becomes more circular, that difference decreases. It might seem obvious that a more elliptical orbit should make the planet much colder when it is farther from the Sun and much warmer when it's closer. But the effect on global annual sunlight is relatively small. Eccentricity matters mainly because it changes how strongly another orbital cycle, precession, affects the seasons. At present, Earth is closest to the Sun in early January and farthest away in early July. That may sound backwards to anyone living in the Northern Hemisphere, where January is winter and July is summer. But the seasons are not caused primarily by distance from the Sun. They are caused by Earth's axial tilt. This is why the Southern Hemisphere has summer while Earth is near its closest point to the Sun. The Southern Hemisphere is tilted toward the Sun at that time, while the Northern Hemisphere is tilted away. The current difference in Earth-Sun distance adds a little strength to Southern Hemisphere summers and slightly reduces the intensity of Northern summers. But oceans and the distribution of land complicate the result. The Southern Hemisphere contains much more ocean, and water changes temperature slowly, which helps moderate its seasons. If Earth's orbit were perfectly circular, the distance from the Sun would remain almost constant, and precession would have less effect on seasonal intensity. When the orbit is more elliptical, the timing of each hemisphere's seasons relative to the nearest and farthest points becomes more important. The second major cycle is obliquity, the change in the angle of Earth's axial tilt. Earth is currently tilted by about 23.5 degrees. This tilt gives us the seasons. As the planet moves around the Sun, one hemisphere leans toward the Sun while the other leans away. 6 months later, their roles reverse. But the angle of the tilt is not fixed. Over a cycle lasting about 41,000 years, it varies between roughly 22 and 24.5 degrees. That difference may seem small. If someone tilted a lamp by 2 degrees, you might not feel the need to record the event in a geological archive. Across an entire planet, however, even a small change in tilt can alter the strength of the seasons, especially at high latitudes. When the tilt is greater, summers become warmer and winters colder, particularly near the poles. More sunlight reaches the high latitudes during summer, and less reaches them during winter. When the tilt is smaller, the seasons become milder. Summers are cooler, and winters are somewhat less severe. For the growth of ice sheets, cooler summers are especially important. A very cold winter can produce plenty of snow, but if the following summer is warm enough, much of that snow melts. The climate can remain cold in winter without building a permanent ice sheet. A smaller tilt reduces summer sunlight in the high northern latitudes. This gives snow a better chance of surviving through the warm season. If patches of snow remain year after year, they can gradually build into larger areas of ice. This is one reason the climate can move toward glaciation even if winters are not becoming dramatically colder. The decisive question is not simply how much snow falls, it is how much remains. Imagine a bank account in which winter makes deposits and summer makes withdrawals. If summer removes everything winter added, the balance returns to zero each year. But if summer leaves a little behind, the account slowly grows. After many centuries, the result can become extremely large, although a glacier is much less useful for paying electricity bills. The third major orbital cycle is precession, the slow change in the direction of Earth's axis. Earth spins like a top, but its axis does not point in exactly the same direction forever. Over about 26,000 years, the axis traces a slow circle in space. Today, the northern end of Earth's axis points roughly toward Polaris, the North Star. Thousands of years from now, it will point toward different stars. Polaris is therefore not permanently assigned to its role. It is simply enjoying a very long shift. Precession changes the timing of the seasons relative to Earth's position in its orbit. At present, Northern Hemisphere summer occurs when Earth is near its farthest distance from the Sun. In roughly half a precession cycle, Northern summer will occur closer to the Sun. When Northern summer happens near the closest point, it becomes somewhat more intense. When it happens near the farthest point, it becomes milder. The strength of this effect depends on eccentricity. If Earth's orbit is almost circular, the nearest and farthest distances are not very different, so precession has a weaker influence. If the orbit is more elliptical, the seasonal contrast becomes stronger. There is also a second component to precession, involving the orientation of the orbit itself. The elliptical path slowly rotates through space. The combined effect of the axial wobble and the rotating orbit determines when each hemisphere receives its strongest seasons. Taken together, eccentricity, obliquity, and precession change the seasonal and geographical distribution of sunlight. They do not greatly alter the total amount of solar energy Earth receives over a whole year. Instead, they redistribute that energy. This distinction is essential. Ice sheets do not respond only to the global annual average. They respond to local conditions, especially summer conditions over large northern land areas. The northern hemisphere contains much more land at high latitudes than the southern hemisphere. Canada, Greenland, Scandinavia, and northern Asia provide broad surfaces where snow and ice can accumulate. The southern hemisphere is dominated by ocean at similar latitudes, apart from Antarctica. Ocean water moves, stores heat, and resists the formation of continental ice sheets. Antarctica already has a great ice sheet, but the repeating expansion of northern ice has been central to recent glacial cycles. For this reason, scientists often pay close attention to summer sunlight around 65 degrees north. This latitude crosses regions where major ice sheets have grown in the past. When summer sunlight there becomes weak, winter snow is more likely to survive. A small area of persistent snow increases the brightness of the surface. Bright snow reflects much of the incoming sunlight back into space rather than absorbing it as heat. This encourages further cooling. More snow survives, more sunlight is reflected, and the frozen area expands. This is the ice albedo feedback we encountered earlier. But the orbital cycles do not simply press a button and produce a glacier. They change the odds. Whether ice actually grows depends on the rest of the climate system. Suppose northern summers become slightly cooler, but atmospheric carbon dioxide is high. The greenhouse effect may keep temperatures warm enough to melt most of the snow. Suppose the same orbital conditions occur when carbon dioxide is lower. ocean circulation is different, and existing ice already covers parts of the north. Then the climate may respond much more strongly. This is why similar orbital patterns do not always produce identical climates. The condition of the planet matters. Ice sheets themselves also influence their own growth. As an ice sheet becomes thicker, its surface rises to higher elevations where the air is colder. This allows more snow to remain. The ice also changes atmospheric circulation. Its height can redirect winds and storm tracks. Dust may increase in some regions and settle on land or ocean surfaces, affecting ecosystems and carbon cycling. At the same time, expanding ice sheets lock up water that would otherwise remain in the oceans. Sea level falls, exposing continental shelves and changing coastlines. Ocean currents may shift as the shape of the basins and the movement of freshwater change. Vegetation moves as temperatures and rainfall patterns alter. Forests may retreat in open tundra, or grassland may spread. Because dark forests absorb more sunlight than bright snow or pale ground, changes in vegetation can strengthen cooling. Carbon dioxide and methane may also decline as oceans, soils, wetlands, and ecosystems respond. Lower greenhouse gas levels allow more heat to escape to space, encouraging further cooling. The original orbital change may therefore be modest, but it can set off a chain of responses that make the final climate shift much larger. The opposite happens when orbital conditions begin favouring stronger northern summers. More ice melts. Darker land and ocean surfaces are exposed. They absorb more sunlight, leading to further warming. Melting ice sheets release fresh water into the oceans, sometimes disrupting circulation. Carbon dioxide and methane rise through processes involving the oceans, soils, and ecosystems. Sea level climbs as water returns to the sea. In this way, orbital cycles act more like a conductor setting the pace than an engine supplying all the power. The larger climate system contains many instruments, and some are much louder than others once they begin. Evidence for the orbital influence comes from several kinds of geological records. One of the most important is found in ocean sediments. Tiny marine organisms live near the ocean surface and build shells from minerals dissolved in seawater. When they die, some of their shells sink and become part of the sediment on the seafloor. The chemical composition of these shells carries information about the temperature of the water and the amount of ice stored on land. By studying long cores drilled from the ocean floor, scientists can reconstruct changes across millions of years. These records reveal repeating patterns that match the timing of orbital cycles. Variations near 23,000 years, 41,000 years, and roughly 100,000 years appear in the climate data. This correspondence became especially convincing during the 20th century, when researchers compared detailed sediment records with astronomical calculations. The match helped establish orbital forcing as a central explanation for the timing of glacial cycles. Ice cores offer another extraordinary record. In places such as Antarctica and Greenland, snow accumulated year after year and compressed into ice. The layers preserve dust, volcanic material, chemical signals, and tiny bubbles of ancient air. Those air bubbles contain samples of past atmospheres. Scientists can measure carbon dioxide and methane from times when great ice sheets covered the north. The records show that greenhouse gas levels changed alongside temperature and ice volume. During glacial periods, carbon dioxide was lower. During interglacials, it was higher. The orbital cycles helped begin the changes, while greenhouse gases amplified them. This partnership explains why the climate response was much stronger than the direct change in sunlight alone. It also reveals a common misunderstanding. Some people hear that carbon dioxide rose after an initial warming at the end of past glacial periods and conclude that it could not have influenced the warming. But cause and feedback can work together. An orbital shift may begin warming part of the planet. Oceans and ecosystems respond by releasing carbon dioxide. That additional carbon dioxide then spreads through the atmosphere and strengthens warming globally. A match can light a fire even though the fire soon releases far more heat than the match itself. Another puzzle appears in the timing of the recent cycles. Eccentricity has a rhythm near 100,000 years, and the major glacial cycles of the last several 100,000 years also show a strong 100,000-year pattern. That sounds like an easy connection. The difficulty is that eccentricity has a relatively weak direct effect on sunlight. Obliquity and precession produce stronger changes in seasonal sunlight at high latitudes. Why then did the climate begin responding so strongly at roughly 100,000-year intervals? This is known as the 100,000-year problem. The answer probably lies in the internal behaviour of the climate system. Ice sheets take time to grow. They can survive several smaller orbital cycles before becoming unstable. Their enormous weight, height, and movement over the land create thresholds. A gradual build-up may continue until orbital conditions, greenhouse gas changes, and ice sheet dynamics combine to trigger rapid melting. The climate can therefore respond in a way that is not a simple copy of any one orbital cycle. Think of repeatedly pushing a heavy object. Each push may be small, but the object does not move smoothly every time. Friction holds it in place until enough force accumulates, and then it shifts. Glacial cycles may behave in a similar threshold-based way. Orbital variations provide repeated changes in seasonal sunlight, while the ice sheets, oceans, and atmosphere determine when a major transition occurs. The geological record also shows that the rhythm changed over time. Between about 2.5 million and 1 million years ago, glacial cycles were more closely connected with the 41,000-year tilt cycle. Then, during the mid-Pleistocene transition, the cycles became longer and more intense. Large ice sheets began lasting closer to 100,000 years. There was no sudden new motion in Earth's orbit to explain this. Something within the climate system changed. One theory suggests that repeated glaciers gradually scraped away layers of soil and sediment from northern continents. Earlier ice sheets may have rested on soft material that allowed them to slide and melt more easily. Once that material was removed, later ice sheets sat on harder bedrock and could grow thicker. Other explanations focus on long-term declines in carbon dioxide, changes in ocean circulation, or the way ice sheets interacted with the land beneath them. The exact cause remains an area of research. What is clear is that orbital cycles do not operate on a passive planet. Earth has a memory. The condition left by one glaciation influences the next. This brings us closer to the question of the future. Astronomers can calculate Earth's orbital variations far ahead with considerable accuracy. The gravitational interactions are complex, but the cycles themselves are predictable across the timescales relevant to the next glacial period. The present orbital configuration does not strongly favour immediate ice sheet growth. Northern summer sunlight is not entering a sharp decline that would normally push the planet quickly toward glaciation. Earth's orbit is currently quite close to circular, so the precession effect is relatively weak. The axial tilt is slowly decreasing, which tends to reduce high-latitude summer sunlight, but the overall combination of cycles matters more than any one movement alone. Some earlier studies compared the present interglacial with one that occurred about 400,000 years ago. That earlier warm period, known as marine isotope stage 11, lasted unusually long. The orbital conditions during that time shared some similarities with the present, especially a low eccentricity that weakened the precession cycle. This suggested that the Holocene might naturally have continued for many thousands of years, even without human influence. Other comparisons pointed toward a glacial inception, perhaps within several tens of thousands of years. Differences arose from the climate models used, the past intervals chosen for comparison, and assumptions about greenhouse gas levels. This uncertainty does not mean scientists have no idea what the future holds. It means the natural onset of a glacial period depends on thresholds rather than a single calendar date. Without human influence, the next major glaciation was probably not due tomorrow, next century, or even in the next few thousand years. It would have unfolded slowly across a much longer interval. The beginning might first appear as slightly cooler northern summers, changes in vegetation, and small areas where snow survived more often. Glaciers in favourable locations could expand. Over thousands of years, those changes might develop into broad ice sheets. There would be no morning when everyone woke up and found the Ice Age had officially begun, complete with a helpful notification on their phones. Scientists looking back from the future would identify the transition through long-term trends. They might choose a point when permanent snowfields began growing, when ice volume crossed a threshold, or when global temperatures entered a sustained decline. The beginning would depend partly on how it was defined. Yet whatever natural timing the orbital cycles might have produced, the atmosphere is no longer following the conditions of earlier interglacials. Carbon dioxide concentrations are far above the range that accompanied the glacial cycles of the last several 100,000 years. That additional greenhouse warming opposes the cooling influence needed for new northern ice sheets to form. The orbital gears are still turning. Earth continues along its changing path. The tilt still varies, the axis still wobbles. Summer sunlight in the north will continue rising and falling, but the climate system receiving those signals has been altered. This is rather like adjusting the timer on a freezer while leaving the door open and placing a heater nearby. The timer is still functioning perfectly. It is simply no longer controlling the result by itself. To see why the present warm interval became so important and why it provided the unusually stable setting in which civilization developed, we need to return to the end of the last glacial period. The great ice sheets did not vanish in one smooth retreat. The climate warmed, paused, shifted abruptly, and warmed again, while oceans rose across landscapes that people and animals had known for generations. What ended that frozen world reveals how orbital changes, greenhouse gases, and climate feedbacks can turn a slow, astronomical signal into a transformation of the entire planet. Around 20,000 years ago, the world was not simply a colder version of the one we know. It was arranged differently from coast to coast. Vast ice sheets covered much of Canada, the northern United States, Scandinavia, and parts of northern Europe. Mountain glaciers were larger on nearly every continent. Sea level stood more than 100 meters lower, because so much of the planet's water had been lifted out of the oceans and stored on land as ice. Britain was connected to mainland Europe by a broad region of plains, rivers, marshes, and low hills. Alaska and Siberia were joined across Beringia. Australia and New Guinea formed a larger connected landmass. Many modern islands were simply high ground overlooking dry coastal plains. The map of Earth would have looked familiar in outline, but the shorelines would have been in the wrong places, which is usually frowned upon by mapmakers. This coldest phase of the last glacial period is known as the last glacial maximum. It did not mean that every part of Earth was covered in snow. Tropical forests survived, although they were often smaller and more fragmented. Deserts expanded in some regions. Grasslands and open steppe covered areas that now support dense forest. The tropics were cooler, the oceans were colder, and the atmosphere held less carbon dioxide than it does today. The Great Northern Ice Sheets contained an extraordinary amount of water. In places, the Laurentide ice sheet over North America was several kilometers thick. Its surface rose high enough to influence winds, storm paths, and regional temperatures. The weight of the ice pressed the crust downward. Beneath it, landscapes disappeared for thousands of years. Along the edge of the ice, meltwater rivers shifted through broad valleys. Dust blew across open ground. Mammoths, bison, horses, reindeer, and other animals moved through cold grasslands. Human groups lived across parts of Africa, Asia, Europe, Australia, and the Americas, adapting to very different environments with clothing, fire, tools, hunting knowledge, food gathering, and strong social cooperation. Then the climate began to change. The end of the last glacial period was not caused by one sudden event. No single volcano erupted, no single ocean current shifted, and no one forgot to close an enormous planetary freezer. The transition began through a combination of orbital changes and climate feedbacks that had been developing over thousands of years. Changes in Earth's orbit gradually increased summer sunlight in the high northern latitudes. The northern hemisphere began receiving stronger summer warmth during the season when ice was most vulnerable to melting. This did not instantly remove the ice sheets, they were far too large for that, but it changed the balance between winter accumulation and summer loss. More snow and ice melted during the warm season. Less remained to replace what had disappeared. At first, the retreat may have been modest. A glacier thinned along its edge. Meltwater flowed for a little longer each summer. Dark patches of ground appeared where bright ice had once reflected sunlight. Those darker surfaces absorbed more solar energy. Bare rock, soil and vegetation warmed more strongly than snow. As more ground was exposed, the region absorbed more heat, encouraging further melting. The ice albedo feedback had helped the ice sheets grow during the earlier cooling. Now it began working in the opposite direction. The shape of the ice sheets mattered as well. Once they started thinning, their surfaces dropped to lower elevations. Air temperatures are generally warmer at lower heights, so the sinking ice surface experienced more melting. A high, cold ice sheet could protect itself to some extent. A lower one became more vulnerable. Changes in the atmosphere amplified the warming. Carbon dioxide concentrations had been low during the glacial maximum. As the climate began to warm, the oceans and land released additional carbon dioxide. The oceans store far more carbon than the atmosphere. Their ability to hold that carbon depends partly on temperature, circulation, biology, and sea ice. As the Southern Ocean and other regions changed, more carbon dioxide entered the atmosphere. This added to the greenhouse effect. The initial orbital warming was strongest in particular seasons and latitudes, but carbon dioxide spread through the atmosphere and helped warm the planet more broadly. Methane also increased. Wetlands expanded as ice retreated and rainfall patterns changed. Microorganisms in waterlogged environments produced methane, another heat-trapping gas. The rise of greenhouse gases did not begin the entire process on its own, but it strengthened the warming once it was underway. The orbit provided the first push, and the atmosphere helped the climate continue moving. This is one of the reasons the end of an ice age can involve much more warming than the direct astronomical change would produce by itself. Earth's climate contains feedbacks. The orbit changes sunlight slightly, ice begins melting, the surface darkens, greenhouse gases rise, oceans shift, vegetation moves, and each response affects the next. The great ice sheets did not retreat at the same speed everywhere. Some regions warmed quickly, others remained cold. Ice advanced again in certain places before resuming its retreat. This uneven behavior is visible in ice cores, ocean sediments, lake deposits, cave formations, and fossil pollen. These records show that the journey out of the last glacial period was not a smooth climb from cold to warm. It included pauses, reversals, and sudden changes. One of the most important parts of this transition occurred around 14,700 years ago, during a rapid warming often associated with the beginning of the Buling-Alarud period. Temperatures in Greenland rose sharply. In some reconstructions, the change happened within decades. Forests began expanding northward in parts of Europe. Glaciers retreated. Rainfall patterns shifted. Animal populations moved into newly available habitats. For people living at the time, the change would not have appeared as a number on a temperature graph. It would have been seen in the movement of plants, the timing of seasons, the disappearance of familiar ice, and the arrival of animals in places where they had not lived before. A valley once dominated by open tundra might slowly gain shrubs and trees. A river fed by melting ice could change course. A coastline might begin advancing inland as sea level rose. The warming released enormous quantities of meltwater. Lakes formed along the edges of the ice sheets, sometimes held back by walls of ice or loose sediment. When those natural barriers failed, floods could rush across the landscape. One of the largest glacial lakes in North America was Lake Agassiz. At different times, it covered parts of what are now Manitoba, Ontario, Saskatchewan, North Dakota, and Minnesota. Its drainage changed repeatedly as the ice sheet retreated and new routes opened. Fresh water entering the North Atlantic could influence ocean circulation. This matters because the Atlantic carries large amounts of heat northward through a network of currents. Warm, salty surface water moves north. As it cools, it becomes denser and sinks in certain regions, helping drive a larger circulation system. Adding large volumes of fresh water can make the surface less salty and less dense, potentially reducing sinking and weakening the movement of heat. This connection between melting ice and ocean circulation appears to have played an important role in abrupt climate changes during the last deglaciation. About 12,900 years ago, after a period of warming, temperatures in the North Atlantic region dropped again. This cold interval is known as the Younger Dryas. The name comes from Dryas octopetala, a small flowering plant adapted to cold conditions. Its pollen and remains became more common in European sediments as tundra-like environments returned. The Younger Dryas was not a complete return to the deepest glacial conditions, and its effects were not identical across the world. But Greenland and much of the North Atlantic region cooled sharply. Glaciers advanced in some mountain areas. Winds, rainfall, and ecosystems changed. The most widely supported explanation involves a disruption of Atlantic circulation caused by fresh water from melting ice sheets, although scientists continue studying the exact routes, timing, and mechanisms. The atmosphere and oceans are closely linked. If the North Atlantic transports less heat, nearby regions can cool even while the planet as a whole remains in a longer-term warming trend. This is a useful reminder that global climate change does not mean every location follows the same path at the same time. A warming planet can contain regional cooling. A melting ice sheet can weaken a current that normally carries heat north. The result can look contradictory until the full system is considered. The Younger Dryas lasted for roughly 12 centuries. That is short compared with an entire glacial cycle, but it is long compared with human history. Many generations were born, lived, and died during it. People adapted to changing plants, animals, water supplies, and seasonal patterns. In parts of the eastern Mediterranean and southwest Asia, communities were already gathering wild grains and living in more permanent settlements. Climate instability placed pressure on food systems, but human responses varied from place to place. It is sometimes said that the Younger Dryas directly caused agriculture. The real picture is more complicated. People have been managing plants, gathering seeds, hunting, and altering local environments long before full farming developed. The colder and drier conditions may have influenced some communities, but agriculture emerged through a long process involving climate, population, social choices, available species, local knowledge, and cultural change. Human history rarely offers one cause when it can provide 12. Around 11,700 years ago, the Younger Dryas ended abruptly. Temperatures in Greenland rose quickly again. The event marks the beginning of the Holocene, the warm interval in which we live. The rapid shift may have occurred as Atlantic circulation strengthened and resumed carrying more heat northward. The exact trigger is still studied, but the ice core record shows that large regional changes can happen surprisingly fast when ocean and atmospheric systems cross a threshold. The end of the Younger Dryas did not mean that all ice disappeared. The Laurentide and Scandinavian ice sheets continued shrinking for thousands of years. Large remnants remained across Canada. Greenland retained its ice sheet. Antarctica remained frozen. Sea level continued rising as meltwater returned to the oceans. The rise was not perfectly steady. At several points, particularly during events known as meltwater pulses, sea level climbed rapidly. One major episode, called Meltwater Pulse 1A, occurred earlier in the deglaciation, around 14,600 years ago. Sea level may have risen by several meters per century during part of this event, though estimates vary. For coastal communities, even a slower rise would have transformed the landscape across generations. Campsites, hunting grounds, river mouths, and freshwater sources were gradually drowned. The people living through these changes did not leave written descriptions. but underwater archaeology and geological mapping reveal portions of the lost terrain. Stone tools, animal remains, and drowned river channels show that the continental shelves were once inhabited landscapes. Doggerland, between Britain and mainland Europe, remained above water for thousands of years after the coldest phase. It supported wetlands, rivers, forests, animals, and human communities. As sea level rose, it became smaller and more fragmented until the North Sea covered most of it. Similar transformations occurred around the world. The Persian Gulf basin flooded. Parts of Southeast Asia became separated into islands. Australia became divided from New Guinea and Tasmania. Beringia narrowed and disappeared beneath the sea. The end of the last ice age therefore created many of the coastlines that now seem permanent. It shaped migration routes, isolated populations, and changed access to resources. It also altered the land far from the sea. As glaciers retreated, they left behind piles of sediment, ridges of debris, deep lakes, carved valleys, and redirected rivers. The Great Lakes of North America are closely tied to glacial erosion and meltwater. Northern Europe contains thousands of lakes occupying basins shaped by ice. Long ridges called eskers mark the paths of rivers that once flowed beneath glaciers. Moraines record places where ice margins paused. Many soils used for farming developed on material moved or crushed by ice. Some regions have fertile glacial deposits. Others have thin, rocky ground where the ice removed much of what had been there before. The crust itself responded to the loss of weight. During glaciation, the heavy ice sheets pressed the land downward. After melting, the crust began rising again through a process called isostatic rebound. This uplift continues today in parts of Canada and Scandinavia. Some coastlines are rising relative to the sea, even while global sea level increases. Old beaches can now be found above the modern shore. The end of the glacial period also transformed ecosystems. Cold steppe and tundra retreated northward. Forests expanded across Europe and North America. Different tree species moved at different speeds, depending on their seeds, climate tolerance, and available roots. Pollen preserved in lake sediments allows scientists to follow this movement. A layer dominated by grasses may be followed by birch, then pine, then oak or other woodland species as conditions warm. Animals moved with the changing vegetation, but not all survived. Mammoths, mastodons, giant ground sloths, and many other large animals disappeared near the end of the Pleistocene. The causes of these extinctions remain debated and probably differed among regions and species. Climate change altered habitats and food supplies. Human hunting and landscape use added pressure. In some cases, small or isolated populations may have been especially vulnerable. The result was a world with fewer very large land mammals. The mammoth steppe, once spread across huge areas of the northern hemisphere, broke apart as wetter climates and forests expanded. For human beings, the warmer Holocene opened some opportunities and closed others. Reindeer routes shifted, coastal areas flooded. Forests made certain forms of hunting more difficult. New plants, fish, shellfish, and woodland animals became available. Communities adapted with different tools and strategies. Fishing increased in many places. Boats became more important. People used grinding stones to process seeds. Some settlements became more permanent. Over time, farming developed independently in several regions, including Southwest Asia, China, New Guinea, parts of Africa, Mesoamerica, the Andes, and eastern North America. The relative climate stability of the Holocene did not make agriculture inevitable, but it provided conditions in which seasonal patterns could become dependable enough for planting and harvesting in many regions. Compared with the large swings of the glacial period, Holocene temperatures were relatively stable on a global scale. There were still droughts, cold intervals, warm periods, volcanic disruptions, and major regional changes. The climate was never perfectly calm. Even so, the broad stability helped support the growth of villages, towns, and eventually cities. Food surpluses allowed some people to specialize in crafts, trade, administration, construction, and organized warfare. Because every achievement comes with paperwork and complications. Rivers such as the Nile, Tigris, Euphrates, Indus, and Yellow River supported large farming societies. Their floods, rainfall patterns, and seasonal cycles became woven into calendars, religions, governments, and daily life. The entire recorded history of civilization fits inside this one interglacial. Every known empire, road network, port, university, industrial city, and railway was built during the Holocene. That does not mean the Holocene was designed for humans. It simply means human societies took shape under its particular conditions. Our farms, reservoirs, houses, and coastlines are adapted to the climate range of this warm interval. This is why changes in climate matter, even when Earth has experienced far greater shifts in the past. The question is not whether the planet can survive. Earth survived the last ice age, earlier greenhouse periods, mass extinctions, and conditions far beyond anything humans have known. The practical question is how quickly ecosystems and societies can adjust. A coastline moving over 10,000 years creates one kind of challenge. A rapid rise over a few centuries creates another. The world created by the end of the last glacial period may feel stable because it has lasted throughout recorded history. But the processes that formed it have not stopped. Earth's orbit continues changing. Ice sheets still respond to temperature. Oceans still transport heat. Greenhouse gases still influence how much energy the planet retains. The same climate system that ended the last glacial period remains active. Under natural conditions, the long orbital rhythm would eventually reduce northern summer sunlight again. Snow would become more likely to survive. Small glaciers might expand. Carbon dioxide and other feedbacks could support a gradual return toward cold conditions. Yet the next glacial period did not begin at the end of the Holocene's first several thousand years, nor is it beginning now. Part of the reason lies in the present orbital arrangement. The combination of eccentricity, tilt, and precession has not produced a strong enough cooling signal for rapid glacial growth. Another part lies in the natural level of greenhouse gases during the Holocene. Carbon dioxide did not fall as low as it had before some earlier glaciations. Then humans began changing the atmosphere on a scale that no previous civilization had attempted. Coal, oil, gas, land clearing, cement production, and agriculture added carbon dioxide and methane. The climate system that once responded to a slow orbital push toward ice now contains much more heat-trapping gas. The end of the last ice age created the world in which civilization became possible. What happened afterward may have changed the timing of the next one because the planet's ancient orbital clock is still moving, but the atmosphere around it is no longer the same. For thousands of years after the great northern ice sheets disappeared, the planet continued moving through the same slow, astronomical cycles that had guided earlier glacial periods. Earth's orbit changed shape. Its axis shifted in tilt. The direction of that axis continued its gradual wobble through space. Summer sunlight in the far north rose and fell just as it had before, and yet the ice did not return. No new continental ice sheet began spreading across Canada. Scandinavia did not disappear beneath kilometres of frozen water. Snow continued to fall each winter. Mountain glaciers continued to grow and shrink, and Greenland remained covered in ice. But the great movement toward another glacial period never properly began. At first, this may seem surprising. The warm Holocene has already lasted for nearly 12,000 years. Some earlier interglacial periods were shorter. If the climate follows a rhythm, it might seem reasonable to expect the cold phase to have started by now. But Earth's glacial rhythm is not a regular ticking clock. It is more like a door that opens only when several conditions line up at the same time. Orbital changes may move the handle, but the atmosphere, oceans, ice sheets and land determine whether the door actually swings open. The present interglacial began under orbital conditions that strongly favoured the melting of northern ice. Around 11,000 years ago, summer sunlight at high northern latitudes was stronger than it is today. This helped remove the remaining parts of the great ice sheets and allowed forests to move northward. Since then, northern summer sunlight has generally declined. That might sound like the beginning of another glacial period. Cooler northern summers should help snow survive, and surviving snow is the first step toward larger ice sheets. The problem is that the decline has been slow and relatively weak. Earth's current orbital shape is close to circular, which reduces the strength of the seasonal changes created by precession. When the orbit is strongly elliptical, the difference between Earth's nearest and farthest positions from the Sun becomes greater. The timing of summer relative to those positions can then make a noticeable difference to seasonal warmth. At present, the orbit is not very eccentric. The difference in distance still exists, but it is not large enough to produce the strongest possible contrast. The slow wobble of Earth's axis therefore changes northern summers less dramatically than it would during a more elongated orbit. This has helped give the present interglacial an unusually gentle astronomical setting. Northern summer sunlight has weakened, but it has not fallen sharply enough to guarantee that large amounts of snow will survive across broad regions. The tilt of Earth's axis is also gradually decreasing. A smaller tilt gives the high latitudes cooler summers, which might encourage ice. But orbital influences have to be considered together. No single movement decides the climate. The exact combination of tilt, wobble, and orbital shape has not created the kind of strong and sustained summer cooling that preceded some earlier glaciations. There is also the matter of timing. A glacial period does not begin the instant summer sunlight starts declining. Ice sheets require suitable land, enough snowfall, cool summers, and long-term support from the rest of the climate system. Northern Canada and Scandinavia may experience severe winters, but most winter snow still melts during summer. Even in regions where snow survives at high elevations, it usually remains confined to mountain glaciers or small ice fields. To begin a continental glaciation, permanent snow would have to spread across large lowland areas. Each year would need to leave behind more frozen water than the year before. The accumulation would have to continue for centuries and then millennia. The first changes would be subtle. Snowfields might remain through unusually cool summers. Vegetation would retreat from certain uplands. Small glaciers would thicken and move downhill. Bright surfaces would reflect more sunlight, cooling the local climate. Eventually, if the conditions persisted, the growing ice could begin changing winds, storm tracks, and regional temperatures. The climate system would reinforce the initial cooling. Nothing like that is happening across the northern continents today. Mountain glaciers in many regions are shrinking rather than expanding. Snow cover is decreasing in many places. Arctic sea ice is becoming thinner and less extensive over the long term. These are signs of warming, not glacial inception. Even without human influence, the natural path toward the next glacial period may have been unusually long. Scientists often compare the present orbital conditions with earlier warm intervals to understand what might have happened naturally. One commonly discussed comparison is an interglacial that occurred around 400,000 years ago. It is known in the marine climate record as marine isotope stage 11. That interglacial lasted for a long time compared with several others. Its orbital setting included low eccentricity, rather like the present. Because the orbit was close to circular, changes in precession had a weaker seasonal effect. The comparison is not perfect. Carbon dioxide levels, ice sheet history, and the exact orbital details were different. Earth never repeats the same climate experiment under identical conditions. Still, the long duration of that earlier warm period suggests that the Holocene might naturally have continued for many thousands of years. Some calculations indicate that without industrial activity, the next strong opportunity for glacial growth might not have arrived for roughly 50,000 years. Other studies have suggested different times, depending on how they define the start of glaciation and which climate thresholds they use. This range can sound frustrating. People often prefer a date. A calendar entry labelled Next Ice Age would be extremely convenient, especially for anyone planning a very long holiday. The uncertainty exists because glacial inception is not triggered by astronomy alone. Scientists can calculate future orbital changes with confidence, but they must also estimate how the climate responds. How much summer cooling is needed before snow begins surviving? How low must carbon dioxide fall? How do forests, sea ice, ocean currents and clouds affect the result? Does a small permanent ice field continue growing, or does a warmer decade remove it again? The answers depend on the starting condition of the planet. At the beginning of earlier glacial periods, large parts of the northern hemisphere were already cool. Atmospheric carbon dioxide was lower, Arctic sea ice was more extensive, mountain glaciers were positioned to expand. The modern world has moved in the opposite direction. The atmosphere contains far more carbon dioxide than it did before industrialization. The oceans have absorbed a great amount of heat. Land and sea ice are declining. This makes the threshold for glaciation much harder to reach. Carbon dioxide is not the only greenhouse gas, but it is especially important because it remains involved in the climate system for a very long time. Methane is more powerful molecule for molecule, but it is removed from the atmosphere much more quickly. Carbon dioxide continues cycling among the air, oceans, soils, plants and rocks across centuries and longer. Before industrialization, atmospheric carbon dioxide was around 280 parts per million. During the coldest parts of recent glacial periods, it fell closer to 180 parts per million. During warm interglacials, it generally rose toward the higher end of that natural range. These changes may seem small because carbon dioxide makes up only a tiny fraction of the atmosphere. But climate does not depend only on which gases are most abundant. Nitrogen and oxygen make up most of the air, yet they do not absorb heat in the same way. Carbon dioxide absorbs certain wavelengths of infrared radiation leaving Earth's surface. It then releases energy in different directions, including back toward the lower atmosphere and surface. Increasing its concentration changes the balance between incoming sunlight and outgoing heat. During past glacial cycles, small orbital changes began the process, while carbon dioxide helped amplify it. Cooling oceans and changing ecosystems reduced atmospheric carbon dioxide. Lower carbon dioxide allowed further cooling. Expanding ice reflected more sunlight. The system moved toward a colder state. For the next glacial period to begin, the northern summer cooling would have to overcome the greenhouse effect already present. Under natural Holocene conditions, this may eventually have happened as orbital cycles changed and carbon dioxide slowly varied. Human activity has raised the barrier. The burning of coal, oil and natural gas transfers carbon that was stored underground into the atmosphere. Cement production releases additional carbon dioxide. Clearing forests removes trees that would otherwise absorb carbon and often releases carbon from vegetation and soil. Agriculture adds methane and nitrous oxide, which also trap heat. The increase has taken place extremely quickly compared with natural glacial cycles. Past shifts between glacial and interglacial carbon dioxide levels unfolded over thousands of years. Industrial societies have produced a much larger change in only a few centuries. The atmosphere now contains a concentration of carbon dioxide far beyond the range found in ice cores covering many glacial cycles. That difference helps explain why the next ice age has not begun, although the earliest human influence is more difficult to identify. Some researchers have asked whether agriculture may have altered the natural climate thousands of years before industrialization. Early farming communities cleared forests, burned vegetation, cultivated rice, and raised livestock. These activities released carbon dioxide and methane. According to one hypothesis, the gradual rise of greenhouse gases during the later Holocene was partly caused by early agriculture and may have prevented a small natural cooling. This idea is sometimes called the early anthropogenic hypothesis. It remains debated. Natural changes in wetlands, oceans, and ecosystems can also explain part of the greenhouse gas pattern, and estimating ancient land use is difficult. Even if early agriculture had some influence, it was far smaller than the effect of modern fossil fuel use. A farming village clearing a patch of forest and an industrial economy burning billions of tons of carbon are not operating on the same scale. The stronger modern influence leaves little doubt that current conditions do not favour a new glaciation. This can create a misunderstanding. If global warming delays an ice age, does that mean it is useful or protective? The answer depends on timescale and consequence. Preventing a glacial period tens of thousands of years in the future does not make rapid warming today harmless. A glacial period would develop slowly enough for coastlines and ecosystems to shift over thousands of years. Modern warming is changing climate much faster. Sea level is rising as land ice melts and ocean water expands. Heat extremes are becoming more intense. Rainfall patterns are shifting. Oceans are warming and becoming more acidic as they absorb carbon dioxide. The distant absence of glaciers across northern Canada offers little comfort to a coastal community facing flooding this century. It is also important to separate the natural glacial cycle from the idea that warming will simply cancel cooling and create a perfectly stable climate. The climate system does not work like two equal numbers crossing each other out. Human greenhouse gas emissions have not placed Earth in a permanent ideal middle state. They have pushed the planet toward additional warming. The farther greenhouse gas levels rise, the greater the warming influence becomes. Natural orbital cycles continue in the background, but their cooling effect over the next several thousand years is small compared with the warming effect of modern greenhouse gas concentrations. A common claim suggests that because Earth was naturally heading toward another ice age, present warming might simply be an early reversal of that cooling. Geological evidence does not support this picture. Global temperature was not falling toward an immediate glacial period before industrialization. There were regional and century-scale variations, including cooler intervals, but no continent-wide expansion of permanent ice was underway. The orbital configuration did not favour a near-term glaciation. Even without modern emissions, the next major cold phase was likely far in the future. Another misunderstanding comes from the idea of a repeating 100,000-year cycle. If major glacial periods often follow a rough rhythm near that length, and the last one ended around 12,000 years ago, perhaps the next one should be approaching on schedule. But the 100,000-year pattern is not a simple countdown between the end of one ice age and the beginning of another. Most of a glacial cycle is spent in the colder condition. Ice sheets grow slowly, remain large through fluctuating climates, and then retreat relatively quickly. The warm interglacial occupies only part of the full cycle. The timing also varies. The climate responds to overlapping orbital changes and internal thresholds, rather than a fixed interval. One cycle may last longer than another. Interglacials do not all have the same length. Earth's climate history resembles a musician following several rhythms at once, not a metronome striking the same note every 100,000 years. The present absence of a new glaciation also reflects the disappearance of the old ice sheets. Large ice masses can help maintain cold conditions. Their bright surfaces reflect sunlight, their height keeps them cool, and their presence reshapes atmospheric circulation. Once the Laurentide and Eurasian ice sheets melted, the planet lost those powerful cooling influences. A future glaciation would have to begin with much smaller ice fields and build them again. Greenland remains frozen, but its location and shape do not automatically lead to ice sheet growth across nearby continents. Antarctica is isolated in the southern hemisphere and surrounded by ocean currents. Its ice affects global climate and sea level, but it cannot simply spread northward across the sea. The Arctic Ocean contains floating sea ice rather than a continental ice sheet. Sea ice reflects sunlight and affects ocean-atmosphere exchange, but because it already floats, its melting does not directly raise sea level in the way melting land ice does. Its decline still matters. Dark ocean water absorbs more sunlight than bright ice. As summer sea ice shrinks, the Arctic warms more rapidly, a pattern known as Arctic amplification. This warming makes nearby land areas less favourable for permanent snow and ice. Frozen soils thaw, snow melts earlier, vegetation changes. These responses move the region farther from the conditions needed for glacial growth. Ocean circulation adds another layer. During glacial inception, the distribution of heat between oceans and continents would need to support cooler northern summers and persistent snow. The Atlantic circulation carries heat northward, but changes in that circulation can create complicated regional effects. A slowdown could reduce some northward heat transport, yet the result would occur within a globally warmer climate. It would not automatically begin a glacial period. For a true glaciation, cooling would need to persist across broad areas and through many summers. Snow accumulation would have to exceed melting for centuries. Small regional temperature changes would not be enough. Volcanic eruptions can cool the climate temporarily by placing reflective particles high in the atmosphere. After a large eruption, global temperature may decline for a year or several years. But volcanic particles fall out, the cooling fades. A few cold summers may expand some glaciers, but they cannot usually sustain continental ice growth without longer-term support. A cluster of eruptions might produce a more noticeable interval, yet the greenhouse gases and orbital conditions would still control the broader direction. Changes in solar activity also affect climate, but the sun's short-term variations are too small to create a new ice age under present conditions. Periods of reduced solar activity can contribute to modest regional or global cooling, especially when combined with volcanic eruptions and ocean changes, but they do not override the long-term greenhouse influence. The climate system is influenced by many forces, but not all forces are equally strong or long-lasting. The next glacial period has therefore failed to begin for two broad reasons. Natural orbital conditions have not yet produced a strong enough cooling signal, and human-added greenhouse gases have made the required threshold much more difficult to reach. The first reason would have delayed the ice under natural conditions. The second has probably extended the delay far beyond that. Climate models suggest that even a relatively moderate amount of human carbon emissions can prevent glacial inception for tens of thousands of years. Larger emissions could delay it for 100,000 years or more. These are not precise appointments. They are estimates based on models of orbital forcing, carbon dioxide, ice sheet growth, and long-term climate response. The future also depends on what happens to atmospheric carbon. Some carbon dioxide will be absorbed by the ocean and land over the coming centuries. A significant fraction, however, remains in the climate system much longer. Over thousands of years, ocean chemistry removes more. Over hundreds of thousands of years, weathering and the formation of carbonate minerals gradually transfer carbon into geological storage. This slow removal means the atmosphere does not simply return to its earlier condition as soon as emissions stop. Even after human civilization changes beyond recognition, the carbon released during the industrial era may continue influencing the timing of glaciation. The orbital cycles of the distant future will arrive, but they may encounter an atmosphere still carrying part of our signal. There is something unusual in this. A species that has existed for only a brief moment in geological time has altered a climate rhythm operating across millions of years. No government planned to delay the next glaciation. No early steam engine designer intended to change the climate of the distant future. Each fire, engine, factory, power station, aircraft, and cleared forest contributed only a small amount by itself. Together, they changed the atmosphere. This does not mean humans have complete control over Earth's climate. Volcanoes will still erupt. Continents will continue moving. The sun will slowly grow brighter over geological time. Ocean currents and ecosystems will keep changing. But within the timescale of the next glacial cycle, atmospheric carbon dioxide has become a major human influence. If greenhouse gas levels eventually decline far enough, and if future orbital conditions strongly reduce northern summer sunlight, ice sheets may begin growing again. The Quaternary Ice Age has not necessarily ended. Antarctica and Greenland still hold permanent ice, so the planet remains within the wider icehouse state. A warmer interglacial can be greatly extended without removing the possibility of future glaciation entirely. Yet, if warming continues for long enough and becomes strong enough to remove most permanent polar ice, Earth could eventually leave the present ice age in the broader geological sense. Whether that happens depends on the amount and duration of warming, the response of the great ice sheets, and the long-term carbon cycle. For now, the next glacial period remains distant. The astronomical signals are too weak, the northern continents are too warm, and the atmosphere contains too much heat-trapping gas. The ancient machinery has not stopped. It is simply operating under new conditions. Earth continues to circle the sun. The axis continues its slow turn. Tens of thousands of years from now, northern summers will again receive different amounts of sunlight. But the outcome will depend on how much carbon dioxide remains above us when those future seasons arrive. That is why the question of the next ice age cannot be answered by orbital cycles alone. To understand how far the cold has been pushed into the future, we need to follow carbon dioxide through air, ocean, forest, soil, and stone, and see how one small part of the atmosphere became powerful enough to interrupt a rhythm older than humanity itself. Carbon dioxide is easy to overlook. It has no colour, no smell, and makes up only a small part of the atmosphere. You cannot watch it gather above a city, or see it drifting from one continent to another. If the sky changed colour every time its concentration increased, the problem might have attracted attention rather sooner. Instead, carbon dioxide remains invisible while quietly helping to control how much heat Earth keeps. This small quantity of gas has played a major role in the advance and retreat of ice for millions of years. It didn't act alone, and it was not usually the first cause of the recent glacial cycles. Changes in Earth's orbit altered the distribution of sunlight, particularly during northern summers. Ice sheets then responded, oceans changed, plants moved, and atmospheric carbon dioxide rose or fell. Once carbon dioxide began changing, it strengthened the direction in which the climate was already moving. During the coldest glacial periods, the atmosphere contained much less carbon dioxide than it did during warm interglacials. Ice cores from Antarctica preserve this history in tiny bubbles of ancient air. Layer after layer of snowfall trapped samples of the atmosphere, allowing scientists to measure gases from hundreds of thousands of years ago. Those bubbles show a repeated pattern. When large ice sheets covered the northern hemisphere, carbon dioxide was low. When the ice retreated and the climate warmed, carbon dioxide rose. Temperature and greenhouse gases move together through cycle after cycle. This does not mean carbon dioxide was the only control on climate, or that every rise began at exactly the same moment as warming everywhere. The climate system is not a row of switches waiting to be turned on in the correct order. It is a network of connected processes, each affecting the others. An orbital change could warm northern summers and begin melting ice. The oceans would respond. Carbon dioxide would increase. That additional gas would trap more heat, spreading and strengthening the warming. The warmer climate would melt still more ice. During cooling, the sequence could work in reverse. Weaker summer sunlight allowed snow to survive. Ice sheets expanded. The oceans and living world absorbed more carbon. Atmospheric carbon dioxide declined, reducing the greenhouse effect and allowing further cooling. Carbon dioxide was therefore both a response and a cause. It reacted to the first changes and then became one of the forces driving what happened next. A fireplace offers a simple comparison. A match may begin the process, but the match does not supply most of the heat. Once the wood catches, the fire becomes far more powerful than the small flame that started it. In the recent glacial cycles, orbital changes were often the match, while greenhouse gases and other feedbacks helped build the larger climate response. To understand why this happens, it helps to look at the natural greenhouse effect. Earth receives energy from the sun mainly as visible light and other shortwave radiation. Some is reflected by clouds, ice, snow, deserts, and the atmosphere. The rest is absorbed by the land and oceans, warming the surface. The warm surface then releases energy upward as infrared radiation. Certain gases in the atmosphere absorb some of this outgoing energy and emit it again in different directions. Part returns toward the surface and lower atmosphere. This process keeps Earth much warmer than it would otherwise be. Without the natural greenhouse effect, the average surface temperature would be well below freezing. The oceans would look rather different, and beach holidays would require extremely determined participants. Water vapour is the most abundant greenhouse gas, but it mostly acts as a feedback. Warm air can hold more water vapour, which strengthens warming. Cold air holds less, which strengthens cooling. Carbon dioxide acts differently because its atmospheric concentration can be altered by volcanic activity, oceans, life, weathering, and human emissions. A change in carbon dioxide can remain long enough to push the climate, after which water vapour responds and amplifies the effect. The natural carbon cycle constantly moves carbon among several major reservoirs. Carbon passes through the atmosphere, oceans, living organisms, soils, sediments and rocks. It can complete some parts of this journey in days and others in millions of years. Plants remove carbon dioxide from the air through photosynthesis. They use the carbon to build leaves, stems, roots, seeds and wood. Animals eat plants or other animals, moving carbon through food webs. Respiration returns much of it to the atmosphere. Decomposition releases more when organisms die. Fires rapidly send carbon from vegetation into the air. Soils store enormous amounts of carbon in roots, dead material, and organic matter. Wetlands can preserve carbon when waterlogged conditions slow decomposition. In other places, warm temperatures and active microorganisms return it more quickly. The oceans exchange carbon dioxide with the atmosphere across their surface. Sometimes they absorb more than they release. Sometimes they release more than they absorb. Cold water can generally hold more dissolved carbon dioxide than warm water. This is one reason warming oceans tend to weaken their ability to take up additional carbon. It is similar to the way a warm fizzy drink loses its gas more easily than a cold one, except the ocean is larger and generally less disappointing at a picnic. Once carbon enters seawater, it takes several chemical forms. Some remains as dissolved carbon dioxide. Much becomes bicarbonate and carbonate ions. Marine organisms use some of this carbon to build shells and skeletons. When those organisms die, part of their material sinks. A small fraction becomes buried in sediments, eventually forming carbonate rocks or organic deposits. Ocean circulation also carries carbon into deep water, where it may remain separated from the atmosphere for centuries. Over much longer timescales, rocks regulate atmospheric carbon through weathering. Carbon dioxide dissolves in rainwater, making it weakly acidic. This water reacts with certain minerals on land. Rivers carry the products toward the oceans, where carbon can eventually become locked into carbonate sediments. This process removes carbon dioxide from the atmosphere, but it operates slowly. Mountain building can expose fresh rock and speed weathering. Warm, wet conditions can also increase chemical reactions. Volcanoes and tectonic activity return carbon from Earth's interior to the atmosphere. Carbon buried in sediments may be carried deep underground where moving plates meet. Some later emerges through volcanic gases. Across millions of years, the balance between volcanic release and weathering removal helps determine whether Earth occupies a warmer greenhouse state or a colder icehouse state. If volcanoes release carbon dioxide faster than weathering removes it, concentrations can rise. If weathering and burial remove carbon faster than it is replaced, concentrations can fall. The arrangement of continents affects this balance. Tropical continents receive abundant warmth and rainfall, encouraging weathering. Large mountain ranges expose fresh rock. Ocean gateways influence currents and the transport of heat and carbon. Life also changes the cycle. The spread of land plants increase the weathering of rock, because roots break surfaces apart and release chemicals into soil. Forests store carbon. while the burial of organic material can remove it from the atmosphere for geological periods. Coal, oil, and natural gas are part of this long story. They contain carbon from ancient organisms that was buried and transformed underground. Coal formed mainly from plant material that accumulated in wetlands and escaped complete decomposition. Oil and natural gas formed largely from microscopic organisms buried in marine or lake sediments, although the full process varies among deposits. For millions of years, much of that carbon remained isolated from the atmosphere. It was not participating in the rapid biological cycle. It had entered geological storage. Industrial society found these concentrated energy sources and began bringing them back to the surface. Burning them combines their carbon with oxygen, producing carbon dioxide and releasing energy. In a few centuries, humans began returning carbon that nature had stored over immense periods. This is different from burning wood in an otherwise stable forest cycle. A growing tree may absorb carbon that previous tree released. If the forest remains healthy and is allowed to regrow, some of that movement can be balanced over time. Fossil fuels add carbon from outside the active surface cycle. The atmosphere, ocean, plants and soils must then find somewhere to place the extra amount. They do absorb much of it. Forests, vegetation and soils take up additional carbon. Oceans absorb a large share as well. Without these natural sinks, atmospheric carbon dioxide would rise even faster. But the sinks do not remove everything, and their help comes with consequences. When oceans absorb carbon dioxide, seawater chemistry changes. The water becomes more acidic, meaning its position on the acidity scale shifts, even though it remains slightly alkaline overall. This reduces the availability of carbonate ions needed by many corals, shellfish, and microscopic organisms. Absorbing carbon therefore limits atmospheric warming, but places additional stress on marine ecosystems. Land sinks can also weaken. Drought, heat, wildfire, deforestation, insects, and soil damage can reduce the amount of carbon stored by forests and vegetation. A region that once absorbed carbon may release more during severe disturbance. The carbon cycle is not an unlimited cleaning service waiting patiently behind industrial society. It can soften the increase, but it cannot make the added carbon disappear on a convenient human schedule. This brings us to one of the most misunderstood features of carbon dioxide, its atmospheric lifetime. It is tempting to ask how many years a molecule remains in the air, as though carbon dioxide has an expiry date printed discreetly on the side. Individual molecules are constantly exchanged with oceans, plants, and soils. One molecule may leave the atmosphere quickly, while another enters to replace it. The more important question is how long the added quantity continues affecting the climate. Some of an emission is absorbed within decades. More is removed over centuries as carbon mixes into the deeper ocean. A smaller but significant portion remains in the surface climate system for thousands of years. The final removal through rock weathering and sediment formation takes much longer still. There is no single moment when all the carbon from an industrial emission vanishes. Its influence fades in stages. This long persistence matters for the next glacial period. Orbital cycles operate across tens of thousands of years. Human carbon emissions, although released quickly, can alter the atmosphere across part of that same timescale. A factory chimney may operate for a few decades. The building may later close, rust, and disappear. Yet a portion of the carbon released during its operation can continue affecting the climate. After the factory, the company, and perhaps the city around it have changed beyond recognition. The natural glacial cycle depended on carbon dioxide remaining within a relatively narrow range. During the recent Ice Age cycles, concentrations rose during interglacials and fell during glacial periods. The difference was large enough to have powerful climate effects, but small enough to be measured in only a few hundred molecules among every million molecules of air. Before widespread industrialization, carbon dioxide had remained near the upper end of the natural interglacial range for thousands of years. Human activity then pushed it far beyond the levels recorded through many previous glacial cycles. The speed of that change is as important as the amount. At the end of the last glacial period, carbon dioxide rose over thousands of years. Ecosystems and oceans still faced major changes, but the transition unfolded far more slowly than the modern increase. Human emissions have compressed a large atmospheric shift into a very short geological interval. Many forests, coral reefs, ice sheets, and ocean systems cannot adjust instantly. Rapid change also makes adaptation difficult for societies. Crops are suited to particular temperature and rainfall ranges. Reservoirs are built around expected river flows. Cities are placed along coastlines based on historical sea levels. Roads, drainage systems, and buildings are designed for familiar conditions. A slowly changing climate allows more generations to move, rebuild, or alter their practices. A rapid shift forces the same work into a much shorter period. The disruption of the glacial cycle is therefore not simply that carbon dioxide has increased. It is that one component of the system has changed so strongly and quickly that the old orbital pattern no longer produces the same result. Under natural conditions, weaker northern summers could have allowed snow to survive. Expanding ice would reflect sunlight. Cooler oceans and changing ecosystems could lower carbon dioxide. The cooling feedback would strengthen. Today, weaker orbital sunlight must compete with a much stronger greenhouse influence. Snow melts earlier, Arctic land warms, sea ice retreats, mountain glaciers lose mass. The first steps required for glacial growth are being reversed. Climate models allow scientists to test this interaction. Researchers can create simulations with different orbital conditions and different carbon dioxide concentrations. They can ask whether snow survives, whether small ice sheets begin forming, and how the result changes as greenhouse gases rise. These studies show that glacial inception is highly sensitive to atmospheric carbon dioxide. When concentrations remain low enough, and orbital conditions strongly reduce northern summer sunlight, ice sheets can begin growing, raise carbon dioxide, and the same orbital conditions may produce no glaciation at all. This means the climate has a threshold. The exact number depends on the orbital arrangement and the model, so there is no universal concentration at which ice either appears or disappears. But the principle is clear. More carbon dioxide requires a stronger astronomical cooling signal to overcome it. The present orbital configuration offers only a weak cooling tendency. The added greenhouse effect easily outweighs it. Even if emissions stopped immediately, the climate would not return to its earlier state overnight. Atmospheric carbon dioxide would decline gradually as land and oceans absorbed more. Temperatures would respond over time. Ice sheets and sea level would continue adjusting. The oceans are especially slow. They absorb heat at the surface and carry some of it downward through circulation and mixing. Because the ocean contains such an enormous mass of water, it stores energy for a long time. This creates a delayed response. The climate can continue changing after the original cause has stabilised. An ice sheet can keep melting because the surrounding ocean remains warm. Sea level can continue rising because deep water and land ice respond slowly. The same inertia operates in both directions. Beginning a new glacial period would require prolonged cooling, strong enough to remove stored heat, rebuild snow, and allow ice to expand. A few cool decades would not be sufficient. Even a century of weaker warming would not automatically restart the glacial cycle. The system would need to cross back through several thresholds. There are also natural feedbacks that could add more greenhouse gases as warming continues. Thawing permafrost allows previously frozen organic material to decompose, releasing carbon dioxide and methane. Warmer wetlands may produce more methane in some regions. Large forest losses can release stored carbon. These feedbacks do not mean that all frozen carbon will suddenly enter the atmosphere at once. The rates and amounts remain subjects of careful study, but they add another reason why avoiding further warming is easier than reversing it after larger changes have occurred. On very long timescales, natural processes will continue removing human-added carbon. Silicate weathering will carry carbon toward the oceans. Sediments will bury it. Tectonic activity will eventually recycle some of it. Given enough time, the atmosphere can return toward conditions in which orbital cycles again dominate glacial timing. But enough time in geology can mean tens or hundreds of thousands of years. By then, human cultures, languages, nations and technologies may be unrecognizable. Continents will have moved only slightly, but rivers and coastlines will have changed. Some modern materials may remain in sediments as evidence of an unusual interval when one species rapidly moved carbon from rock into air. Future geologists, whether human or something else, might find a thin layer containing plastics, industrial ash, altered carbon chemistry, radioactive traces, and the fossils of domesticated animals. They may identify it as the point when the climate departed sharply from the pattern of earlier cycles. They would see that orbital changes continued exactly as expected. The astronomical rhythms did not fail. The atmosphere changed around them. There is an odd contrast in the timescales. The industrial era feels long when measured through families, inventions, wars, and cities. Against the full glacial cycle, it is extremely brief. Yet that brief interval has been powerful enough to influence when ice sheets may next grow across a continent. The machines that caused the change were ordinary by modern standards. Engines turned, furnaces burned, electricity flowed, vehicles moved people and goods. None looked capable of altering a planetary rhythm. The influence emerged from accumulation. Each release added a little more carbon. The total remained in the atmosphere and oceans. A small gas changed the planet because the emissions continued year after year. This is also why individual weather events cannot tell us whether the greenhouse effect is operating. A cold winter does not mean carbon dioxide has stopped trapping heat. A hot day does not prove the full climate trend by itself. Weather moves quickly. Climate is the pattern formed across many years and regions. A person can roll two low numbers while using loaded dice. The important effect appears after many throws. Greenhouse gases load the climate system toward greater heat, even though individual seasons continue varying. The disruption of the Ice Age cycle is one of the clearest examples of this long-term influence. The next glaciation was never due within a few years or centuries, but the conditions needed for it have been moved farther away. The extent of that delay depends on future emissions. A limited addition of carbon could delay glacial inception for tens of thousands of years. A much larger release could prevent it through more than one favourable orbital cycle. Eventually, the orbit would again reduce northern summer sunlight. The axial tilt would change. Precession would place the seasons in a new arrangement. But if carbon dioxide remained high, the snow would still melt. The astronomical opportunity would pass without producing a great ice sheet. Later cycles might bring another opportunity. By then, more carbon could have been removed naturally. The climate could begin moving toward a colder state once again. This raises an unusual possibility. Humans may not have ended the Quaternary Ice Age, but we may have caused it to skip one or more expected glacial periods. Whether that counts as a permanent change depends on how far into the future we look. On a timescale of tens of thousands of years, the delay may appear enormous. On a timescale of millions of years, it may look like a temporary interruption. For the people living now, however, the immediate concern is not the missing ice sheet of the distant future. It is the warming already underway. Carbon dioxide has altered the planet in a direction opposite to glaciation. Ice is retreating from mountains and polar regions. Oceans are rising. Heat is accumulating. Weather patterns are shifting. The next great freeze has become less likely, while the consequences of a warmer world have become more immediate. That does not make the future simple. Global warming will not raise temperatures evenly. Some places will warm faster. Ocean circulation may change. Rainfall belts may move. A region can experience unusual cold even as the global average rises. The climate system remains restless, filled with local variations and delayed responses. But beneath that complexity, the energy balance has shifted. More heat is being retained than released. Until that imbalance is reduced, the planet will continue moving away from the conditions needed to grow new continental ice. The remaining question is how far this human influence can reach. Can modern warming merely postpone the next glaciation? Or can it prevent the return of northern ice through several orbital cycles? Could the great ice sheets of Greenland and Antarctica eventually shrink enough that Earth leaves its current icehouse state altogether? The answer depends on how much carbon is released, how long it remains, and how the slow parts of the climate system respond. To follow that possibility, we need to look beyond the warming of the next century and imagine Earth after thousands of years, when today's emissions are part of ancient history but the orbital clock is still turning. Global warming can delay the next deep freeze, and the delay may be far longer than a few centuries. The greenhouse gases released during the industrial era are not simply warming the years immediately ahead. They are changing the conditions under which future orbital cycles will operate, which means their influence may still be visible when today's cities, roads, and national borders are very distant parts of history. The basic reason is straightforward. A new glacial period needs cool summers in the northern hemisphere. Winter snow must survive through the warmer months, gather year after year, and eventually form permanent ice. Higher concentrations of carbon dioxide make those summers warmer, increasing the amount of snow that melts and raising the astronomical threshold required for ice sheets to begin growing. Under natural conditions, the present interglacial was probably not about to end soon. Earth's current orbital arrangement does not strongly favour glaciation. Even without human emissions, the next major opportunity for large northern ice sheets may have been tens of thousands of years away. With modern greenhouse gas concentrations, that opportunity has been pushed farther into the future. Depending on how much additional carbon humanity releases, the next glacial period could be delayed for 50,000 years, 100,000 years, or possibly beyond several favourable orbital arrangements. This is a remarkable result when we consider how quickly the change occurred. Glacial cycles unfold over tens of thousands of years. Industrial emissions rose sharply within only a few centuries. A brief event on the geological calendar has altered the likely timing of a climate process much older than our species. To understand how scientists estimate this delay, imagine a graph showing two slow forces. One line represents the amount of summer sunlight reaching the high northern latitudes. It rises and falls as Earth's orbit and axis change. Another line represents the level of carbon dioxide needed to prevent snow from surviving under those sunlight conditions. When northern summers receive less sunlight, glaciation becomes easier. The atmosphere can contain a little more carbon dioxide while still allowing ice to grow. When northern summers receive stronger sunlight, carbon dioxide must be much lower before permanent snow can survive. Glacial inception occurs only when the combination crosses a threshold. Summer sunlight must be weak enough, and greenhouse gas concentrations must be low enough for winter snow to remain. The threshold is not a perfectly sharp line. Ice sheets interact with vegetation, clouds, ocean currents, sea ice, and the shape of the land. But climate models consistently show the same broad relationship. High carbon dioxide makes glacial inception more difficult. During the coldest parts of recent glacial periods, atmospheric carbon dioxide was much lower than it was during warm interglacials. Those low concentrations supported cooler temperatures and helped maintain enormous ice sheets. Before industrialization, carbon dioxide stood near the upper part of its natural interglacial range. It was not low enough to suggest that a glacial period was beginning. Human emissions then moved it far above the range recorded across the recent sequence of ice ages. The orbital cycles continued as before, but the climate moved farther from the freezing threshold. Suppose a future orbital configuration reduces summer sunlight in northern Canada and Scandinavia. Under the atmosphere of an earlier interglacial, snow might have survived in some regions. Small ice caps could have formed, reflected more sunlight, and encouraged additional cooling. Under an atmosphere containing much more carbon dioxide, the same summer sunlight may still produce enough warmth to melt the snow. The favourable orbital moment passes without an ice sheet forming. After many thousands of years, another orbital opportunity arrives. By then, natural processes may have removed some of the excess carbon. If concentrations remain too high, that opportunity may also pass. In this way, global warming can cause the climate system to skip a glacial period, or perhaps more than one. Earth's orbit does not pause and wait for the atmosphere to catch up. The cycles continue whether the ice responds or not. The length of the delay depends heavily on cumulative emissions. This means the total amount of carbon released matters more for the distant future than the emissions of any single year. If humanity sharply reduces emissions, the total addition to the climate system will be smaller. Carbon dioxide will still remain elevated for a long time, but natural sinks will gradually lower it. If large-scale fossil fuel burning continues for many decades, the total release becomes much greater. More carbon enters the oceans and atmosphere, and a larger fraction remains long enough to influence future orbital cycles. This is why scientists cannot give one exact date for the next glacial period. The answer partly depends on choices that have not yet been made. There are also uncertainties in the long-term carbon cycle. Oceans absorb carbon at different rates depending on circulation and chemistry. Rock weathering varies with temperature, rainfall, vegetation, and exposed mineral surfaces. Ice sheets may respond differently as coastlines and ocean temperatures change. Even with these uncertainties, the overall conclusion is clear. Higher greenhouse gas concentrations delay glaciation. Some climate simulations suggest that under natural conditions, a significant glacial inception might have occurred in roughly 50,000 years. With a large industrial carbon release, the delay could extend to at least 100,000 years. These figures should not be treated as countdowns. No one can mark a day on a future calendar and announce that the glacier will begin after breakfast. They describe broad timescales and likely climate states. The start of glaciation would itself take thousands of years. There would be no single winter when the world crossed from interglacial to ice age. Snowfields would expand gradually. Mountain glaciers would thicken. Vegetation zones would move. The changes would become unmistakable only when viewed across many generations. The idea that global warming prevents a future ice age can sound beneficial when stated without context. A continental glacier covering cities would obviously create difficulties. Canada and northern Europe are generally more useful when they are not hidden beneath several kilometres of ice. But the comparison is misleading because the two changes occur at very different speeds. A natural glacial period develops slowly. The initial expansion of snow and ice takes thousands of years. Ecosystems migrate, rivers shift, coastlines fall gradually as water becomes trapped on land. Human societies would face enormous challenges, but they would also have long periods in which to move and adapt. Modern warming is occurring far more rapidly. Temperature, rainfall, sea level, ocean chemistry, and extreme weather are changing within the lifespan of infrastructure and communities. The threat is not that Earth is becoming warm instead of cold. The threat is the speed and scale of the change away from the conditions under which modern societies developed. It would be like avoiding a very slow-moving obstacle thousands of kilometres ahead by turning sharply into a much closer one. Technically, the first problem has been postponed. This does not make the immediate direction sensible. Another source of confusion is the possibility that global warming could weaken major ocean currents and produce cooling in parts of the North Atlantic. If northern Europe became cooler, might that begin the next glacial period despite the rise in greenhouse gases? Ocean circulation can certainly alter regional climate. The Atlantic system carries warm water northward and returns colder, denser water at depth. A weakening of this circulation could reduce the amount of heat delivered to parts of Europe and the North Atlantic. Some regions might warm more slowly than the global average. Particular areas could experience cooler conditions, altered storms, or changed rainfall. This would not necessarily create a glacial period. A continental ice sheet requires broad, persistent summer cooling over thousands of years. Regional cooling caused by an ocean circulation change would occur within a planet retaining more heat overall. The surrounding oceans, atmosphere and land would still contain the influence of elevated greenhouse gases. Snow might increase in some places, but most of it would continue melting during summer. The same applies to dramatic claims that melting Arctic ice could suddenly produce a new ice age. Freshwater can influence ocean circulation, and the climate can respond abruptly in certain regions. But an abrupt regional shift is not the same as the slow growth of continental ice. The last glacial period contained sudden warming and cooling events, particularly around the North Atlantic. These happened because the climate was already in a cold state with enormous ice sheets, extensive sea ice, and low greenhouse gas concentrations. The modern starting point is very different. Large volcanic eruptions can also cool the planet temporarily. Fine particles high in the atmosphere reflect sunlight, reducing surface temperatures for a few years. Several major eruptions close together could create a longer cool interval. Yet these particles eventually fall from the atmosphere. Unless a sustained forcing remains, the cooling fades. Carbon dioxide continues trapping heat after the volcanic effect has disappeared. Volcanoes release carbon dioxide as well, but modern volcanic emissions are much smaller than human emissions. They are essential to the geological carbon cycle over millions of years, but they do not explain the rapid rise of atmospheric carbon during the industrial era. A period of reduced solar activity would face the same limitation. The sun varies slightly, and those variations can influence climate, but the expected changes are not large enough to overcome the warming produced by modern greenhouse gas concentrations. Neither a quiet sun nor several cold winters would restart the glacial cycle under present conditions. The atmosphere must remain cool enough for ice to accumulate over many centuries. A temporary drop in temperature may increase snow or slow glacier loss, but it does not reverse the long-term energy imbalance. There's another question hidden inside the discussion. Could global warming delay glaciation forever? On human timescales, a delay of 100,000 years is almost impossible to distinguish from forever. Every known civilization has existed within only a small fraction of that interval. Geologically, however, 100,000 years is not permanent. Earth's orbital cycles will continue. Carbon dioxide will slowly be removed through ocean processes, sediment burial, and rock weathering. Given enough time, the greenhouse influence of today's emissions will weaken. If permanent polar ice remains and future orbital conditions become favourable, another glacial period may eventually begin. The word eventually is doing a great deal of work here. The continents will still be recognisable after 100,000 years, but coastlines, ecosystems and rivers may have shifted. Human societies may have changed in ways we cannot sensibly predict. After several 100,000 years, tectonic movement will have carried continents a little farther. Evolution will have altered species. Future observers may know the industrial era only through a thin chemical layer in sediments. The ice sheets will also influence whether Earth remains within its present ice age. As long as permanent continental ice survives in Antarctica and Greenland, the planet remains in an icehouse condition. If warming persists long enough to remove much of that ice, Earth could move toward a more complete greenhouse state. This would be a much greater change than delaying one northern glaciation. Antarctica contains enough ice to raise global sea level by many tens of meters if it were all lost. Greenland contains enough for several more meters. Complete melting would take a very long time, particularly in Antarctica, and it is not expected to occur suddenly. But ice sheets respond over centuries and millennia. Once parts of them begin a sustained retreat, they can continue changing long after atmospheric conditions stabilize. Their vulnerability depends on more than air temperature. Warm ocean water can reach floating ice shelves and melt them from below. Ice shelves act as restraints on glaciers flowing from the land. When they thin or collapse, land ice can move toward the sea more quickly. Bedrock shape matters as well. Some glaciers rest on ground that slopes downward inland. As their edges retreat, the ice can become exposed to deeper water and greater instability. These processes make the distant future sensitive to the level and duration of warming, not only the temperature of one particular year. If humanity limits warming and atmospheric carbon dioxide gradually declines, much of the great polar ice may survive. The present ice age would continue, although its next glacial period would still be delayed. If very large amounts of carbon are released and warming persists for thousands of years, the planet could lose enough permanent ice to alter the wider icehouse state. The future is therefore not a choice between global warming and an immediate ice age. It contains a range of possible climates determined by emissions, carbon removal, ice sheet response and natural cycles. At the lower end, human influence extends the Holocene-like warmth and postpones glacial inception. At the higher end, warming reshapes polar ice, sea level, ecosystems, and the long-term climate state. Some people have wondered whether future societies could deliberately manage carbon dioxide to prevent glaciation. If humans or their descendants remain technologically capable tens of thousands of years from now, they might detect the first signs of orbital cooling and release greenhouse gases in a controlled way. In principle, only a relatively small carbon adjustment might be needed to prevent snow from surviving under marginal conditions. This would be a far more deliberate intervention than the uncontrolled emissions of the industrial era. But predicting the abilities and priorities of societies 50,000 years in the future is not really climate science. It is speculation on a scale that makes next month's plans seem wonderfully dependable. Future people might remove carbon rather than release it. They might live under entirely different economic systems. They may have moved populations away from regions vulnerable to ice. They may value a cooler climate for reasons we cannot imagine. The distant possibility does not solve the modern problem. The atmosphere is being altered now, and the consequences are already unfolding. There is also no need to preserve high carbon dioxide today as insurance against an ice age. The next natural glaciation was not imminent. Future societies would have thousands of years of warning as snowfields and ice caps began expanding. They would not need us to leave behind a warmer planet on their behalf. The idea of protecting distant descendants from glaciers by continuing fossil fuel use is rather like leaving the oven on to keep a future resident warm during a winter several thousand years away. The future resident may appreciate the thought, but the present house is likely to have other concerns. Scientists study the delayed ice age not because it justifies warming, but because it demonstrates the reach of human influence. Carbon emissions are powerful enough to change climate beyond the usual timescale of policy, economics, and recorded history. A ton of carbon released today contributes to near-term warming. It also enters an ocean and atmospheric system that will continue adjusting for centuries. A fraction of its influence may persist until future orbital conditions arrive. That makes the industrial era unusual in Earth's history. Earlier organisms altered the planet too. Cyanobacteria transformed the atmosphere by producing oxygen. Land plants changed weathering and carbon storage. Marine organisms built enormous deposits of carbonate rock. Humans are not the first life form to influence global climate. We may be the first to understand that we're doing it while the change is still underway. The ability to understand does not provide perfect control. Climate models have uncertainties. Ice sheets contain thresholds that are difficult to predict. Ecosystems may respond in unexpected ways. But uncertainty does not erase the basic direction. Adding carbon dioxide warms the climate. More cumulative emissions create a larger and longer-lasting influence. That influence delays the return of the northern continental ice. The next deep freeze has therefore not been cancelled by a single decision. It has been postponed through the accumulated result of energy use, industry, agriculture, and land change. How long the postponement lasts remains partly open because the total emission has not yet been decided. If future emissions fall rapidly, the atmospheric disruption will be smaller, although still long-lived. If emissions continue at high levels, the next glacial opportunity may pass without ice forming. The warm interval could extend through another complete orbital cycle. Eventually, natural carbon removal may lower greenhouse gas levels enough for the astronomical rhythm to regain control. Cooler northern summers could once again allow snow to survive. Ice fields could spread outward from mountain regions and high plateaus. The first signs would be small compared with the ice sheets that followed. A permanent patch of snow would remain in a place where summer once removed it. Glaciers would flow farther down their valleys. Forests would retreat from northern ground. Across many generations, these separate changes could connect. The surface would brighten, temperatures would fall, more water would become ice, and sea level would begin a slow decline. Whether that begins in 50,000 years, 100,000 years, or much later will depend on the atmosphere inherited by that distant Earth. The next part of the story therefore lies far beyond the modern warming era. It begins when carbon dioxide has slowly declined, orbital cycles again favour cool northern summers, and the first lasting snow starts to gather. From there, the planet would not simply become colder. Coastlines, rivers, forests, migration routes, and entire regions of human settlement would be rearranged as the ice gradually returned. The return of continental ice is so distant that no one alive today will see its beginning. Neither will our children, their children, or any civilization we can sensibly imagine in familiar terms. Even the earlier stages may lie tens of thousands of years ahead, and modern greenhouse gas emissions may have pushed them farther away still. That makes the question difficult to answer with a date. Scientists can calculate the future changes in Earth's orbit, but they cannot know exactly how much carbon dioxide future societies will release, how quickly natural processes will remove it, or how the great ice sheets will respond over many thousands of years. A reasonable estimate is that, without human influence, the next major opportunity for glacial growth might have arrived in roughly 50,000 years. With the carbon dioxide already added to the climate system, and especially if large future emissions continue, the next glacial period may be delayed for 100,000 years or longer. These figures are not predictions in the same sense as tomorrow's weather forecast. They describe possible climate states under different assumptions. A glacier does not appear because a calendar reaches the correct year. It begins only when the combined conditions allow more snow to gather than summer can remove. The timing depends on Earth's orbit, axial tilt, atmospheric carbon dioxide, ocean circulation, vegetation, and existing ice. All of them have to move far enough in the same direction. Even then, the beginning would be easy to miss. The first sign of a future glacial period would not be a wall of ice moving toward a city. There would be no single winter when the planet suddenly became white. Instead, small changes would accumulate in northern regions. Summer temperatures would become slightly cooler. Snow would remain longer on mountain slopes and high plateaus. A few patches might survive through years when they once melted completely. Those surviving snowfields would grow thicker as each winter added another layer. The weight of the snow would compress the lower layers into dense ice. Small glaciers would begin moving slowly downhill. At first, the changes might look local. A mountain glacier would extend farther into a valley. A permanent ice field would appear on a northern upland. The tree line would move south or downward as growing seasons shortened. A few centuries later, several ice fields might connect. Their bright surfaces would reflect more sunlight, cooling the surrounding region. The ice would rise in height, and the air above it would become colder. Storm tracks would shift. More snow might fall over the expanding frozen ground. What began as a modest response to cooler summers would become a larger climate feedback. This is how a glaciation grows. The ice does not conquer the land through speed. It changes the conditions around itself until expansion becomes easier. The first permanent ice would probably form in places already suited to cold conditions. Mountain ranges, Arctic islands, northern Canada, Greenland, and parts of Scandinavia could become centres of accumulation. Greenland might act as an important surviving core. It already holds a continental ice sheet. although its future size depends on the amount of warming that occurs before the climate eventually cools again. If much of Greenland's ice survives the warmer millennia ahead, it could influence nearby temperatures and snowfall. If most of it disappears, a future glaciation would have to rebuild ice from a smaller beginning. Northern Canada offers broad areas where ice sheets grew repeatedly in the past. Much of the land is high enough and far enough north for snow to accumulate under a cooler climate. Scandinavia could support another expanding ice centre. Mountain glaciers might thicken and spread outward until they merged into a larger sheet covering parts of northern Europe. The growth would take thousands of years. During that time, people or other future observers would see the environment changing, generation by generation. A settlement built near a mountain glacier might find the ice slightly closer every century. Forests would retreat. Rivers fed by meltwater would become larger during summer and smaller during winter. The growing season would shorten. Some crops would no longer ripen reliably. Animals adapted to warmer forests would move south, while cold-tolerant species expanded into the region. These changes would not occur evenly. Some places would cool more quickly than others. Ocean currents would continue moving heat. Winds would carry moisture in changing patterns. One region might receive more snow, while another became colder but drier. Heavy snowfall is essential for ice sheet growth. A place can be extremely cold and still support little ice if not enough moisture reaches it. Antarctica provides the clearest example. It is the coldest continent, but much of its interior receives very little snowfall. Ice exists there because what falls rarely melts and can remain for immense periods. Future northern ice sheets would also depend on snowfall as well as temperature. Areas close to moisture-bearing oceans might accumulate ice more quickly than dry continental interiors. As the ice sheets expanded, sea level would begin to fall. Water would evaporate from the oceans, fall as snow, and remain trapped on land. At first, the decline would be slow and difficult to distinguish from ordinary coastal changes. Over thousands of years, however, the amount of water stored in ice could become enormous. During the last glacial maximum, global sea level stood more than 100 meters lower than today. If future ice sheets reached a similar size, coastlines would move far outward across continental shelves. Shallow seas would become dry land. Islands would connect with nearby continents. River systems would lengthen as they flowed across newly exposed plains toward the retreating ocean. The North Sea would shrink. Britain could once again become connected to mainland Europe by land, although the exact shape would depend on the size of the ice sheets and the movement of the crust. The English Channel might become a broad river valley. Parts of the seabed around Southeast Asia would emerge, joining islands into larger land areas. Australia and New Guinea might once again become connected across the exposed shelf between them. The Bering Strait could close as sea level fell, reconnecting Siberia and Alaska. Animals and people might cross a new version of Beringia, although the environment would not necessarily match the grassland of the last ice age. Modern ports would be left inland. Coastal cities would no longer stand beside the sea, assuming they still existed in anything like their present form. New coastlines would form many kilometres away. Harbours, canals and shipping routes would have to move. The exposed seabed would slowly develop soils, rivers, wetlands and vegetation. This sounds strange because we think of coastlines as permanent boundaries. They are printed on maps, marked by roads and surrounded by buildings. But coastlines are temporary results of the amount of water in the ocean and the shape of the land. During a glaciation, the map would change again. The growing weight of the ice would press down the crust beneath it. Northern Canada and Scandinavia would slowly sink under the load, while areas beyond the ice margin might rise slightly. This bending of the crust would affect local sea level. A coast near the edge of an ice sheet might experience the ocean differently from one far away. After the ice eventually melted, the depressed land would begin rising again, just as northern regions are still rebounding from the last glaciation today. The ice would also reshape the landscape as it moved. Glaciers are not static blocks. They flow under their own weight, although usually so slowly that the movement is invisible without careful measurement. The base of an ice sheet can grind across rock, carrying sand, gravel and boulders. It can deepen valleys, polish surfaces, and scrape long marks into bedrock. Material frozen into the ice would be transported hundreds of kilometres. When the ice melted, it would leave ridges, plains, and scattered boulders far from their original source. Rivers would be blocked or redirected. Lakes would form along ice margins. Some would drain gradually. Others might burst through natural barriers and send enormous floods across the land. A future map of northern rivers could become almost unrecognisable. Water might be forced southward by an ice sheet. New channels would cut through weak points in the landscape. The drainage of entire continents could shift. Lakes could grow where valleys became blocked. Other basins might empty as the ice created new routes. The Mississippi River system was influenced by earlier glaciations, and future ice could alter it again. Rivers in Europe and Asia would respond in similar ways. Far beyond the edge of the ice, the climate would still change. Temperatures would fall across much of the world, but not every place would become frozen. Tropical regions would remain warmer than the poles. Forests would survive near the equator, although many would shrink or move as rainfall patterns changed. Some tropical areas might become drier. Grasslands and savannas could expand where rainforest retreated. Mountain glaciers would grow in the Andes, Himalayas, East Africa, and New Guinea. Deserts might expand in some regions because colder oceans would release less moisture into the atmosphere. Other places could become wetter as winds and storm paths shifted. The last glacial period produced large areas of cold, dry grassland across Eurasia and North America. These environments supported mammoths, horses, bison, reindeer, and other large animals. A future glaciation would not recreate exactly the same ecosystems. Many Ice Age species are extinct. Modern plants and animals occupy different ranges. Human activity has altered forests, soils, rivers, and habitats across the planet. Evolution would also continue during the thousands of years before the ice returned. New species would appear, while others disappeared. The future cold world would be built from the organisms available at that time, not from a preserved collection waiting to restore the Pleistocene. There might be no mammoths unless humans or future descendants of humans recreated something similar through biotechnology. Even then, releasing large hairy elephants onto a frozen plain would be only the beginning of the practical arrangements. Reindeer, musk oxen, cold-adapted birds and northern predators might expand southward if they survived the warmer period before the cooling. Forest animals would retreat with the tree line. Plant communities would move at different speeds. Grasses and small shrubs could spread quickly. Trees would move more slowly because each generation must grow, reproduce, and establish new forests farther south. Some species would become trapped by cities, farmland, mountains, or oceans. Human-built landscapes could make natural migration more difficult than it was during earlier climate cycles. The people of the distant future would face choices no earlier glacial population encountered. If advanced technology remained available, societies could monitor the ice centuries before it threatened major settlements. They might move cities, redirect rivers, build new agricultural regions, and transport food across continents. Energy systems could provide heat, light, and indoor food production. Nuclear power, renewable energy, fusion, or technologies unknown today might make cold climates easier to inhabit. Buildings could be designed for extreme snowfall. Transport routes might cross or pass beneath ice. Some communities might remain close to the growing glaciers for scientific research, mining, water, or simple attachment to their homeland. People have a remarkable ability to remain in places that outsiders consider inconvenient. Other populations would move south. The migration could be gradual because the ice itself would advance slowly. A city might have centuries to plan its relocation. The greater challenge could come from changes in rainfall and food production far from the ice. Agricultural zones would shift toward lower latitudes. Regions that are productive today might become too cold or dry. Other areas could gain milder conditions, deserts might receive new rainfall, land currently too hot for certain crops might become suitable. Human adaptation would depend less on the average global temperature than on the distribution of water, fertile soil, energy, and political cooperation. A slow environmental change does not guarantee a peaceful response. Societies can struggle over small shifts when resources, borders, and institutions are involved. Yet the timescale would offer opportunities. Unlike rapid modern warming, a natural glacial descent would unfold across many generations. Knowledge could be passed forward. Infrastructure could be rebuilt in stages. Future people might even decide to stop the glaciation. If they understood the climate system and controlled powerful technologies, they could raise greenhouse gas levels deliberately. A relatively small increase in carbon dioxide might be enough to prevent snow from surviving during a weak orbital cooling. They could release stored carbon, alter the reflectivity of land, manage forests, or use other forms of climate intervention. This would present difficult questions. Who would decide the desired global temperature? A warmer climate might benefit northern regions while harming tropical ones. Preventing sea level fall would preserve some coastlines, but drown land that would otherwise emerge. Climate management would affect everyone, including people not involved in the decision. The engineering problem might be easier than the political one, which has been a recurring feature of human projects. It is also possible that future societies would welcome some cooling. After thousands of years of warming, a gradual decline in temperature might reduce heat stress in parts of the world. They might try to manage the climate within a chosen range rather than allowing a full glaciation or preventing all natural cooling. Such control would require a level of long-term coordination that modern civilization has not yet demonstrated. Maintaining a climate policy for 10,000 years would be slightly more demanding than agreeing on where to hold next week's meeting. Another possibility is that humans will no longer exist in their present form when the ice returns. Our descendants may have evolved, changed themselves technologically, or spread beyond Earth. Civilization may rise and fall many times. Languages, religions, nations, and economic systems may disappear and be replaced. A future intelligence studying the first new ice fields might not think of the industrial era as recent history. It could appear as an ancient geological disturbance marked by a rapid rise in carbon dioxide and a long delay in glaciation. If no technological civilization remained, life would continue responding without anyone measuring the change. Forests would move, rivers would shift, animals would migrate, ice would grow. Earth experienced glaciations long before humans appeared. It does not require observers, climate conferences, or particularly well-organized filing systems. The ice would eventually reach a maximum size when accumulation and melting found a new balance. That could take tens of thousands of years. At its greatest extent, the future glacial world might resemble the last one in broad outline, but not in every detail. The exact orbital conditions would differ. Continental positions would have shifted slightly. Atmospheric carbon dioxide might not fall to the same level. The ice sheets could be smaller or larger. They might follow different paths across North America and Europe. Ocean circulation could produce a different pattern of regional temperature. After remaining large for thousands of years, the ice would eventually begin retreating again. Orbital cycles would strengthen northern summers. Melting would expose dark land. Carbon dioxide might rise. The warming feedbacks would return. Sea level would climb. Newly exposed coastal plains would flood. Glacial lakes would drain. Forests would move north. Another warm interglacial would begin, although it would not necessarily be identical to the Holocene. The climate rhythm would continue because no glacial period is permanent. Earth has moved between cold and warm states many times, and each state contains the conditions that eventually help produce the next change. Ice sheets alter carbon, oceans, land, and sunlight. Their presence makes the world cold, but orbital cycles eventually place them under stronger summer warmth. Warm interglacials reduce ice and raise greenhouse gases, yet slow carbon removal and future orbital changes can eventually create another opportunity for cooling. This does not make the climate perfectly cyclical. Continents continue moving. the sun slowly changes. Mountain ranges rise and erode. Life alters the atmosphere. Over millions of years, the background conditions shift enough to change the rhythm or end it entirely. The Quaternary Ice Age will not last forever. At some point, Earth may enter a warmer geological state with little permanent polar ice. Much later, new continental arrangements could allow another ice age to begin. The next glacial period is only one movement within that much longer history. For the present, the ice is not advancing. Greenland and Antarctica are losing mass. Mountain glaciers are retreating in many regions. Sea level is rising rather than falling. The climate challenge facing modern society is warming, not the arrival of northern continental ice. Still, asking when the next ice age will begin helps reveal the scale of our influence. Human emissions have not merely changed temperatures for a few decades. They may have altered a natural rhythm across tens of thousands of years. The orbital cycles continue turning with no awareness of us. Earth's axis tilts and wobbles. The planet moves around the sun. Future northern summers will become weaker and stronger according to the same slow pattern. But the atmosphere receiving that sunlight now carries the result of industrial activity. Long after individual carbon dioxide molecules have moved through forests and oceans, part of the added carbon will remain within the system. That legacy may be enough to carry Earth safely past the next astronomical opportunity for glaciation. The snow will fall in winter, melt in summer, and fail to begin the slow accumulation. Another opportunity will arrive many thousands of years later. By then, natural processes may have lowered carbon dioxide. If the northern summers are cool enough, the first lasting snow may finally remain. It could begin on a high plateau in Canada, a mountain range in Scandinavia, or an Arctic island. No one would recognize it as the start at first. It would look like an ordinary patch of old snow that had survived a mild summer. Another winter would cover it. The following summer would leave part of it untouched. Slowly the layers would thicken. Centuries would pass. The patch would become an ice field. The ice field would join another. Glaciers would flow outward, changing rivers and pushing vegetation aside. The world would enter a transformation too slow for one person to witness, but powerful enough to rearrange continents. For now, that frozen future remains very far away. The next deep freeze has not vanished from Earth's story, but its place in the story has been moved. It may wait for one orbital cycle, several cycles, or a much longer clearing of carbon from the atmosphere. And so, after following the planet through ancient glaciations, orbital wobbles, melting ice sheets, rising seas, and the carbon released by modern civilization, we return to the question we began with. How long until the next ice age begins? The honest answer is that no exact year can be given. Naturally, it was probably tens of thousands of years away. Under the atmosphere humans have created, it may be at least 100,000 years away, perhaps longer. Long before then, Earth will pass through other changes that matter far more to the people living through them. Coastlines will respond to present warming. Ecosystems will move. Ice sheets will continue changing. Human societies will decide how much more carbon enters the air. The distant ice will wait while the nearer climate takes shape. Perhaps by now the room around you feels a little warmer than it did when we began. Or perhaps your tea has completed its own journey toward room temperature. Wherever you're listening from, the planet beneath you is moving through several clocks at once. There is the clock of weather, changing from day to day. There is the clock of climate, unfolding across decades and centuries. And beneath them is the slow orbital clock that measures its time in tens of thousands of years. For the moment, the great glaciers remain in the past and the far future. Between them lies the world we know, temporary, changing, and shaped by choices being made now. If this long journey through Earth's frozen rhythm brought you some calm, curiosity, or a quieter place to rest your thoughts, you might like the video and subscribe to Just About Earth. It helps these slow stories reach other listeners who enjoy exploring the planet without having to hurry. The ice will return one day, unless the world changes enough to keep it away. But not tonight, not tomorrow, and not for a very long time. So settle a little deeper, let the distant glaciers remain distant, and rest here in this brief warm interval, while Earth continues its patient journey around the sun.